Ladies and gentlemen, we'll be starting in 2 minutes. We'll be starting in 1 minute. Please be seated. Distinguished guests, Assalamu alaikum and good morning. Welcome to the Kuwait Fourth Flow Measurement Technology Conference. My name is Abdullah Sudan, Senior Public Relations Officer, and I will be your host for today. Before we begin, I'd like to take this opportunity to share a safety moment with you in the unlikely case of an emergency. Please make note of the 2 exit doors on the sides of the stage, on the right and on the left. We begin our ceremony with a blessed recitation from the Holy Quran.
بسم الله الرحمن الرحيم علم القرآن خلق الإنسان علمه البيان الشمس والقمر بحسبان والنجم والشجر يسجدان والسماء رفعها ووضع الميزان ألا تطغوا في الميزان وأقيموا الوزن بالقسط ولا تخسروا الميزان.
Ladies and gentlemen, the 4th Kuwait Flow Measurement Technology Conference follows the great success of the 3 conferences held in 2014, 2015, and 2017. The conference is considered as a major networking event in the Middle East region, emphasizing on flow measurement technology in the oil and gas industry. The conference will be held for 3 days, starting from today, featuring presentations and exhibition covering numerous related topics. Professionals and speakers will be highlighting the latest innovations and services. I would now like to invite KOC CEO, Mr. Imad Sultan, on stage to deliver the welcoming speech.
Bismillah ar-Rahman ar-Rahim. Distinguished guests, respected colleagues, ladies and gentlemen. On behalf of Kuwait Oil Company, all conference chairs, committees, presenters, and delegates, I'm pleased to welcome you all to our country and to this international conference, the Kuwait Fourth Flow Measurement Technology Conference. Thank you for the interest you have shown by coming to this unique gathering from near and far to take part in the presentations and discussion over the coming 3 days. Similar to previous edition, this year also Kuwait Oil Company is the official sponsor of this conference along with other international O&G companies. This premier event focuses on practical application and research studies related to the flow measurement technology in oil and gas industry. It's a matter of pride and strength for KOC to transform into a more effective as well as more efficient exploration and production company. Flow measurement of the different fluid involved in this process of hydrocarbon exploitations play an important role in the quest of transformation due to the associated economic, safety, environmental, and legal impact. In line with this, and as part of our 2040 strategy, we thrive on the sharing of knowledge to reach excellence, mainly by staying ahead of development related to technology, regulations, and practices, amongst others. Several initiatives are in place to empower sharing of knowledge and organize the Kuwait Fourth Flow Measurement Technology Conference, with participation of other K companies and leaders and specialists from NOC and IOC is one such initiative. I'm very much impressed by the wealth of international and national expertise you all bring into this conference and the spectrum and the important issues covered by the 38 papers being presented here, over and above the exhibition platform provided. The subject range from description of new techniques associated with the hydrocarbon flow measurement, quality assurance, and metrology. I'm sure the topics being presented will provide you with a better insight and opportunities for sharing knowledge and ideas. The conference will also be concerned with the importance of hydrocarbon analytical quality, a topic increasing awareness and investigations, uncertainty of measurement, traceability, and metrology of the measurement process need to be considered in the context of global trade. Exchange of information need to be trustworthy, recognizing that reliable international measurement standards often underlie legal and economic decisions. The industrial exhibition by manufacturers, supplier, and O&G companies showcase their latest products, technologies, and services, and offered you the chance to get up-to-date information in your area of interest. I'm confident that this conference and exhibition will provide an ideal and unique environment of networking with key personnel from regulators, operators, manufacturers, research institutes, and engineering fraternity to enhance knowledge and find possible solutions to many challenges encountered in the area of flow measurement in the O&G sector. Real challenge lies in sustaining the achievement and improvement of our performance. Last but not least, I strongly hope that all the distinguished guests will offer their generous support and encouragement for the success of the Kuwait Fourth Flow Measurement Technology Conference. Once again, I'm most grateful for your participation and support in this event. I wish you all of a great time and learning and advancement. Thank you very much.
Thank you, Mr. Imad. Now I'd like to invite Chairman of the Technical Committee, Mr. Rashid Al-Marri, Export Technical Services Team Leader, on stage to deliver the conference speech.
CEO, Kuwait Oil Company, and Conference Chairman, Mr. Imad Sultan. Deputy CEO, West Kuwait Oil Company, Head of Steering Committee, Mr. Mohammed Al-Zabi. Deputy CEO, Services, Support Services, Kuwait National Petroleum Company, KNPC, and member of the Steering Committee of the conference, Mr. Abdulaziz Al-Daij. Distinguished guests, dear audience, Assalamu alaikum wa rahmatullahi wa barakatuh. In view of the great success experimented in the previous three editions of Kuwait Flow Measurement Technology Conference held in the 2014, 15, and 17, plus your strong support, active participation demonstrated during those events, I am so pleased today and highly honored to welcome you all to Kuwait Fourth Flow Measurement for Technology Oil and Gas Conference, which will be held for 3 consecutive days starting from today. Through the successful completion of the previous 3 editions of Kuwait Flow Measurement Technology Conference and Exhibition, about 1,000 delegates and participants, 60 international companies has attended these events. Many flow metering manufacturer, 100 plus author of high technical presentation and field studies cases related to flow measurement, staff from Kuwait University, numerous indirect personnel required for the organization and coordination work, has made this Kuwait Flow Measurement Conference to become an icon and a demanded conference to KBC, K companies, regulators, bodies, NOC and IOCs, manufacturers across the world in the hydrocarbon measurement field. Generous sponsorship from many industrial companies and research organizations from around the world have recognized the Kuwait Flow Measurement Technology Conference is an important venue to discuss scientific and technological collaboration across the GCC and other Middle East countries. Our expectation is to be able to gather about 350 plus participants for today's event, including topics, presenters, directors, representatives, innovators, operators, research institutes, and engineering companies. A total of 38 high technical presentations will be displayed by several international companies, out of which 10 presentations will be delivered by Kuwait Oil Company. Recognition to this technical conference by other external sponsors such as Emerson, Intertek, Honeywell, Weatherford is a proof of the quality and importance of such event. All these factors has contributed to consolidate to this conference as a huge gateway to access the latest technology, recent research and product in the flow measurement area. The quality of the technical presentation is a world class, and the spectrum of the topic is very current and broad. It includes descriptions of new quantitative practices associated with hydrocarbon flow measurement, quality assurance and metrology. I am sure the selected topics will provide you with a highly important information and many opportunities for discussion. Part of KOC pride and strength is our emphasis on the statement that there is always room for improvement, and it is essential for us all to make every effort to better our upstream and downstream method of production, in this case in the hydrocarbon flow measurement. Success is not a matter of desire, going far beyond that, doing more than others expect, is what we strive to do, approaching bit by bit toward excellence. The conference steering committee and the technical committee have worked extremely hard the whole year to prepare an outstanding conference, an impressive roster of distinguished eminent speakers from national oil companies and international oil companies, manufacturers, consultants, engineering companies, research institutes has been assembled for opening ceremony. I'm confident that this conference will be of great benefit to all of us, and I hope you all enjoy the different presentation and other activities scheduled to be covered during the coming 3 days. Once again, welcome all to Kuwait Fourth Flow Measurement Technology Conference and Exhibition, and I wish all success to the participants.
Thank you, Mr. Rashid. Moving on to before we start the exhibition, I'd like to kindly ask Mr. Rashid back on stage and Mr. Imad Sultan also for the honoring of the steering committee and the sponsors. We'll start off with the steering committee, moving on to the sponsors with us today. Mr. Mohammed Al-Zabi. تفضل. We can hear a round of applause. Mr. Abdulaziz Lid'aj. Mr. Shamlan Al-Rumi. And Mr. Rashid Al-Marri with us on stage. Mr. Badr Al-Hadiyah. And Miss Noura Sola. Moving on to the sponsors for this year's conference. Emerson. If we can hear for them a round of applause. Thank you. Intertech. Honeywell. And our last sponsor, Weatherford. Thank you, Mr. Imad. For the second part of the honoring, I'd kindly like to ask DCO West Kuwait, Mr. Mohammed Zabi, back on stage for honoring the participating exhibitors and the technical committee. Starting off with the technical committee, Ms. Mahal Houti, Mr. Abdullah Dabbous, Mr. Ali Ligraini, Mr. Barak Al-Kandiri, Mr. Divin Madakara, Mr. Fawaz Al-Dhafiri, Mr. Henry Gomez, Mr. Jasim Al-Mulla, Mr. Khalid Al-Tuwari, Mr. Kanagasabe Sabapati, if he's here with us today. Moving on, Mr. Khalid Swaidan, Mr. L.R. Krishnan. Mr. Lawson Ramsey. Mr. Louis Tia Garage. Mr. Mishari Al-Hindal. Mr. Nishant Jan Bandu. Mr. Raja Hanna. Miss Mahsouma Nasser. Last but not least, yours truly, Abdullah Sudan. Thank you, Mr. Mohammed. Thank you, Mr. Rashid. Ladies and gentlemen, I would now like to invite Mr. Imad Sultan and his distinguished guests for the official opening of the exhibition of the 2019 Kuwait Fourth Flow Measurement Technology Conference. With this, we will have a 30-minute break. We'd then like to see you back here in the hall for the two presentation segments that we have, which will be managed by the technical committee members, and ending the first day with a luncheon. Thank you very much. Test. Ladies and gentlemen, we'll be starting in 5 minutes the presentations. If you can kindly return to your seats. وعندك presentation صح؟ اوكي. 5 minutes. هسه عشان هو لنا it's a half an hour break. فيعني we're trying to push it early شوية. 10 تبي نبلش؟ I was just informed we'll start in 15 minutes. Just to let you know, we'll start in 15 minutes. I think it's up to their personal preference. I don't know.
Both are ready. Which one?
Okay. Who should somebody?
Where are you? I'm there sitting. Otherwise, I'm staying.
Thank you, sir. Oh.
When you put it off, this is the switch.
Test. Okay.
Now
Ladies and gentlemen, we'll be starting in 1 minute. If you can kindly return to your seats. Thank you all for returning back to the hall. We'll start the second segment of today's conference. In the beginning, we'd like to start before the presentations with the honoring for the participating exhibitors. I'd like to ask Mr. Rashid Al-Marri on stage to give the awards. We'll be calling first for Herman. If they're here with us today, for Herman. Okay. We can hear for them a round of applause, kindly. Thank you. Thanks to all the participating exhibitors with us today. Next is Flexim. Flexim. Thank you. And Omni. Kanar. And finally, Aben. Thank you very much. Thank you, Mr. Rashid. We can now start the presentations. I leave the mic for the technical committee. Ms. Mahal Houti will be handling this session. Thank you very much.
Good morning, all. So as our colleague said, we'll start off first with the first technical topic, challenges to calibrate on-site 212 barrels prover by water draw method, is going to be presented by Mr. Hussein Al-Budin. I'm just going to give you a brief bio about him. He graduated from California State University in Electrical and Electronics Engineering in year 2011. He joined KOC since 2013 as an export engineer. Then he moved to loss control engineer in export oil movement and measurement team. So we're going to present him soon. You might come.
Yes. Assalamu alaikum. Sabah khair. Thank you, Ms. Ma. Our topic today is challenge to calibrate on-site 2012 barrel prover by water draw method. Before I start, I will give you a short story. My father used to buy a fish from the market. One day, the guy who was there asked him to deliver the fish to his house. So my father agreed to do that. This exercise happened for the 2 years. One day, my father decided to buy his own scale. So when the guy came to our home, he brought him the fish. He asked him, this is an 8 kilo fish. So my father took it and scaled it. He found it's a 6 kilo. So my father questioned him, are you sure about your measurement or actually about your scale? The guy was like struggle and said, no, that's fine. Take it as 6 kilo. So from this story, we can say, have you ever asked how accurate these scales? When you go to any market, any place to buy anything, did you ask how this measurement is accurate? But in crude oil markets, we have a different story here. The first question came from the customer, is your measurement is accurate? So he asked you to prove it. Please prove that. The custody transfer metering system contain, if you can see the prover on the left side, containing the meters. So let me explain to you what is the prover. The prover is a device which will be calibrated through a system to determine the volume on it. What is a prover? A prover is a device that validates the measurement system meters against unknown calibrated prover, the volume, calibrated volume, which is called the prover. What proves the prover? Now, let's back to the chain. All the measurement worldwide came back to one measure item, which is what they call it the original kilogram. Please, can you go to the... First, can you go back, please? Let me explain for you the chain first. It's started from the original kilogram, goes to the metrology lab, which is owned by the government. That goes to the test measure. The test measure will calibrate the field prover, which goes to the meters. So, please, original kilogram. The original kilogram is an international prototype kilogram cylinder from platinum, which is kept in France. And all the measurement worldwide came back to this 1 kilogram. Back. Go to the test measure. This is the test measure. It's a small can, contain a volume, which is calibrated back to the metrology lab, owned by the government, goes back to the original kilogram. If you can see, it's from up to down. It's all calibrated with a specific volume. And if you can see the right side, the scale, in case it's reading up for above 100 gallon, which is the size of the can itself, plus 5 or 3 inch above. Back. Why it's important? This is the basic equation to write the bill of lading for any dispatch figure through meters, which is the meter factor, the volume prover, meter volume. If you can see clearly that in case of any error or any bias happen in the prover volume, it will directly impact your measurement, which will be reflecting in your figures, in your money-wise, up or down. How it's performed? On the site, we brought a fresh water, then we have the pump. This is the prover from the top side. Okay? So the quantity goes from the fresh water to the pump, goes to this prover, the calibrated side, goes to the test measure, which will be counted as we explained before, the can size plus the quantity, which will be in the scale. The calibrated volume will be between these two detectors. When it is hit from A to B, this is the volume, what you call it, the calibrated volume. How it's performed. First, we need to isolate the prover and verify the leaks on the four-way valve. Clean the prover and prepare it for fresh water. Validate the detector switch because it's hit the detector switch. Validate the sphere size and inflation. Please, can you go? The sphere, between the two detectors, there is a sphere which will be traveling. And by hitting the detectors, it will be start counting the volume. So this sphere should be inflated between 2 to 5. So nothing will be passed through the, like this, should be traveling in this way. So without any passing after it. So it will hold all the volume behind it. Otherwise, you will have an issue with your figures. Back. Venting the system, you need to get all the air from the system. At least 3 consecutive calibrating run. That means all the repeatability criteria. A run must be performed in different flow rates. Fast, low, fast. So in case of any passing or any issue with With a sphere, it will be shows by changing the flow rate. The corrected volume of the 3 consecutive run should be agreed with the range of 0.020%. Now, why is it a challenge to calibrate 212 barrels? Prover base volume is 212 barrels, which equal to 9,000, almost 9,000 gallons. Each can handle 100. So imagine how many can we require? 1, 2, 3, 4, 5. So actually we required 90 cans per volume. So meeting all the calibration criteria required, minimum of 3 consecutive runs on different flow rates, the volumetric quantity required, it will be this quantity. Imagine, should be done on site with a margin of error of 0.02% repeatability, which equal to 1.8 gallon. So these tankers should have a measurement uncertainty with this limit. Imagine how accurate this system. Calibration V21, which is the prover, what we have in Sea Island. Since factory water withdrawal in 2001, this activity has not performed on site. Only master meter method was performed frequently to validate, calibrate the metering skid. On 2017, KOC decided to calibrate the prover on 2 volumes, A and C, BD, because we have both 2 detectors, so 4 detectors, so they can back each other's, to be backup. With challenging, considering this challenging, each run least minimum 16 hours, pre-run and run. So per day, we were working a minimum of 16 hours on site. Ambient temperature challenge, because it's Kuwait. Location inside the Ahmadi refinery. The in-out for refinery was a trouble. Preparation and setup and cleaning the prover. Since it's in 2001, no one cleaned it. It was very challenging to clean it. There's some pictures from it. This is the cans and how we perform it. Okay, let's give a field experience. Calibrate the first volume, A and C. On-site observation. The sphere was not able to move due to flow rate limitation. When we brought the system there, the sphere, we couldn't bump it. So the sphere was stuck. So what was our solution? To have a bigger bump that required different hoses and generators. We try again. The first 4 consecutive runs were out of repeatability, and we suspect the sphere. So we pull up the sphere. Please, can you go? Hyperlinks. Yeah, this is the sphere. We check it. We check the measurement of it, and to check the 2 to 5% inflation. So nothing will be passed through this sphere, or it should, or it cannot be stuck. Can you back? So we check the measurement of it. We re-inflate it and bring it back. Still, repeatability was not achieved after 5 runs. So we decide to fixing back the old detector, which were removed. As a result, repeatability were achieved. This activity took 11 runs, which we performed in 24 days since we start. Then we go to calibrate the second detectors, which is B and D, on-site observation. After 3 runs, the repeatability was not achieved, and we were noticed the color has been little changed for the water. So we decide to take the sphere out and refill the system with a new fresh water. What was the issue in that? Overhead crane was not available to electrical motor failure. So job was postponed until fixing the issue. After fixing the issue and bringing it back, repeatability was not achieved due to 4-way valve leaking, 1 liter in 5 hours. After we check, we suspect the slips, and we check it to replace it. Can you go to the hyperlinks? Yes. After we check the 4-way valve, we found some rust on the 4-way valve body due to the color of changing of the water. But the slip was in good condition. So we cleaned it and brought it back. Can you go back? Okay. So after removing the rust and clean it, the valve was still passing. So what we decide? We decide to bypass the four-way valve by spading it and utilize the drain point to drive the flow back and forth. So 4 rounds were performed and different were obtained. We did the swabbing in the hoses happening in this way. So we found that we believe that while swabbing the hoses, the air was entering the system. Can you go back? So we think that the air will contain the obtained result, which is up and down, up and down. So we decide to remove the air from the system. Can you go? So swabbing the hoses inside the water. So we brought a bath and just swab the hoses inside the water. So nothing will come from the air. All will be inside the water. Okay, repeatability was achieved. This activity took 2 runs, were performed in 17 days since we fixed the crane. Water draw result. The difference in historical volume compared to 2017. This is the difference in volume between master meter in 2015 and 14. We can see the increment by 0.0279%. And if you can see it, it's almost matching the 2001 result. Why this is important to have a higher volume? This is the mathematic easily. If you have a prover volume is higher, you will have your meter factor is higher, which reflect on your gross standard volume, which will be back as a money. So a conclusion. Lesson to be learned. Sometimes one problem has a multiple reasons, so please be always prepared. Water draw on site is never be easy. Think out of the box to solve these issues. KOC benefits from this. Improves the measurement system accuracy, since we are using the water draw method. Improve KOC revenue, because changing on the 4th decimal will be highly appreciated if you are dispatching something with 7 figures per day. Thanks. Any questions?
Thank you, Mr. Hussein.
So
So we'll just take a few questions. We'll be limited to the questions, so you can ask him during the break time as well.
Hi, good presentation. Quick
you.
question. What was the total time from starting the water draw to completing the water draw, time duration from start to finish?
3 months.
Did you say 3 months?
Yeah.
Thank you.
Last question, if any. All right. Thank you.
Thank you.
Thank you, Mr. Hussein, for your PowerPoint. Before you leave, we'd like to give you a recognition certificate.
Thank you.
I will hand over the mic to Mr. Khalid. He's another committee member, and he will present the other technical presentation.
Thank you, Maha. Good morning, ladies and gentlemen. Our next speaker is Sulaiman Al-Anizi. Sulaiman Al-Anizi, in the beginning of his career, he worked at Doha East Power Station in the Ministry of Water and Electricity as an operation engineer. In 2006, he was hired by the KMBC in the maintenance department, instrument maintenance division, for 13 years. And he has worked in various planet areas at the Mina Al-Ahmadi. Currently, he's operating as a gas plant senior instrument engineer.
So this will.
Yes, please.
Okay. I guess. Yeah. Okay.
Mr. Suleiman, you have 15 minutes.
Yeah.
The stage is yours.
Thank you very much for the great introduction. So I'll start. Okay. Okay. I would like to present today the case study flow measurement accuracy loss and gain. You know, we had a problem, and coming back from a maintenance background, problems is the reasons for our existence. Well, to solve them, not to cause them, right? What was the problem? In the previous years, KMBC had a potential loss of approximately $500,000 during the ship loading at the oil pier on the selected meter in the performance analysis. The root causes of the loss were investigated and identified, and remedial causes were implemented. To solve the problem, the oil pier metering system was replaced with a system based on the international API standard. New procedures, recommendations based on the analysis were followed, taking into consideration several contributors, including fluid properties. This resulted in accurate representation of the fluid quantities dispatch. We had an issue. We replaced the meters. We have implemented a new procedures recommendation. Did we solve the problem? Of course, in real life, we will still have some challenges. Okay, the standard meter loading report are not being officially used by the oil account. However, the tank dip method and the manual calculation of specific gravity at 60 Fahrenheit was still used to issue the final loading account calculation certificate for the customers. So now, still we did not use the new meter system for the calculations. Maybe it's because of the lack of confidence on the meters. Maybe it's because there's so many parties involved. So based on the management directive, a team was formed including all the concerned members to analyze the performance of the new oil beer metering system. We have 121 liquid meters and 17 LPG meters, and come up with a recommendation. We wanted to analyze and see why it's happening and what was the difficulties that we faced. So the team reviewed the complete system and observed that the LPG meters for 1 and 2 are not calibrated proof due to the valve passing and ice formation in the provers. Based on the above, the team decided to separate the review. So they have reviewed one as liquid and the other one as the LPG. So the LPG portion was reviewed later after the valve repair. And then after the review of the liquid meter system, the team selected the skid 416 naphtha for the performance analysis. There were 3 batches. As we see, I'm not sure how we point here, but anyway, so we have 3 figures. One is from the KMBC metering figures, and the other from the ship figures, and the other one from the shore. And now, seeing the differences gave us a confidence on our meters. You know, we have a loss in all cases. If we would have gone with the meter, that would be definitely a profit for us. So that's allow us also to see the differences and gain a confidence on the meters. For the land loading, is the same thing. We have 58 metric tons and a loss of 22,000. Then we came up with a recommendation. So also because it's crucial to have the focal point. It's crucial to be on time. Every steps throughout the loading, it counts. So we have said operation shall act as a single metering focal point for coordination between the operation and the other related divisions that include oil account, instrument maintenance, process control, and lab. Make a procedure and guidelines for the starting the batch, sampling, proving, end batch, lab data, and obtain the final report. Set a standard calibration. For the export meters, calibration shall be every quarter. For the land loading, that would be every 6 months. So all the recommendations were implemented. The loss was recovered. However, there will be always a room for improvement. So that improvement include analyzing the data, because with the time you have a huge chunk of data, and that data you could have utilized to know where are we today. So this is what we did. We had these are data. We put them in a statistical model, and then this model tell us basically if you notice that if I can solve the point. No. Okay? This one? No. Anyways, no. Okay, here. So the money is here, and this line is before the data. This line is before the data, and the other one is after the change. So now how would I reduce it again? Can we? Yeah, just make it smaller. Yeah. So now the value, the difference between the KMBC and the shore on the horizontal line, the difference between the KMBC and the ship on the vertical line, and the horizontal line down is the year. So the change was implemented in October 2017. So before the change, we noticed that the variation was higher. It comes to a similar mean after the change, when the shore and the ship, they're confirming that both are negative. And when the ship and the shore, they are confirming that the difference is positive, that mean, yes, it was increased, but that will be due to the accuracy and the higher range of the meter itself. And then, it's become all right at the beginning of this year. Okay, here the change of the the differences, the probability of difference to be positive. If you notice that the no, that is before the change, and yes is after the change was implemented. So the differences, the probability that the difference is positive is more after the change than it's before the change, and that proved that the change was impact the outcome. So here I put the same. We put also the same points. In the negative wise and the positive wise. The negative after the change, we noticed that the change was in the other direction. So basically, in the negative, if you see the mean and the standard deviation was lower on the negative side. On the positive side, the mean and the standard deviation is more, and that is capturing more value to KMPC. So here is the decision tree. The decision tree is another model that is very useful to explain relationships between the data, even if the data they don't have prior model, or they are not meant to be on one relationship in terms of statistical data. So in that input, you could feed a lot of input. Basically, this is the main things. This is the main input that I used. However, I have not included, for example, the absolute values, the numbers. I have not included maybe the year that the ship was made on, and maybe the skill of the workers, maybe the operation that handling the loading at the time. So here it is. So I add the ship line, the berth, which meter package, the product, and the absolute difference between the KMBC ship and the shore. So with that model, okay, with that model, it's an experimental model approach. Means that that model can tell us, can identify the opportunity, such as which ship liner would take the shore reading to verify. Or for some ships liner, the model would indicate that we better take the shore reading, that the red means the positive value and the blue means the positive value and the red means the negative value. However, we have noticed that the meter package play a lesser percentage in difference. So for example, if I came here and I say, okay, I'll say that when I'm here, I'm sure that the value would be negative. And that for most cases in this ship. And that is a statistical probability. When I come here and I say, okay, I'm sure that the ship, if I compare the readings to the shore, I will get a positive value. So that will be a gain for me. So I have I have the prediction beforehand that whether, okay, I'll go with this ship will cause me a trouble. This ship is good. This ship I rather take a shore reading. This ship I can rely on the meter on it. So this is like it's an experimental thing. We get some result. We try to compare and then make some correction again, and then we keep developing ourselves using the data we have throughout the years. So as a conclusion, obtain the confident flow measurement would define repeatability and reproducible figures against certain condition of measurement like fluid properties, distribution of velocity, etc., which in return help gain client accreditation. And the second point, that the statistical data analysis help us deeper understanding of the flow meter reading, which in return increase the KMPC profitability. That's it. Thank you very much.
Thank you, Mr. Sulaiman.
Thank you very much.
Any question, please?
Yeah.
Go Ali. My question is the last thing that you mentioned as a model experiment, where you tell your experience with this ship. Do you use it also in calculation like the VAF, or you only use it just to decide what you should expect when you are loading this vessel to be prepared?
Yeah.
Assure your tank figure with the meters.
True. We thank you for the question. It's a very good question. However, we are obligated to use by the KPC to use the meters now. We don't go for the dip unless we have to, or there is a dispute. The value is about 3%. But this figures we are developing the confidence on the model. So basically, we run a lot of models and we pick the one that suits us with the time. So sometimes we'll say this model will give us like 80% correct. This model will give us, we have, it was not right in this time, or it was not right next time. So we tune it until we got the almost a 90% that we are confident that this ship will cause that, and this ship will cause this. However, we are not really using it for anything. It's just for us to have the sense and have the feeling. And once you feel the data, you will have kind of direction where you're heading. Whether you can trust your meters more, you can know your customers more as well, or you can see operation. You guys, whenever these ships are coming and it's your time, there is something wrong. What we're doing wrong? Is there everything all right? That's how it is. It's guidance more than reference.
Okay, appreciate it. Thank you very much.
Thank you.
Any last question, please? Thank you, Mr. Sulaiman.
Thank you.
Thank you so much.
Okay. يعطيك العافية. الله يعافيك. مشكور. الله يعطيك العافية.
I will leave the floor again to my colleague.
مشكور. الله يسلمك. Okay, let's.
Hello again. Can we get the audience in front instead of being all the way back? If you can just come in front of us so you can see and you can ask the questions. Thank you. All right, so now we're going to start the third technical topic, which is combination of uncertainties for multi-stream metering systems. That will be presented by Mr. David Woods. He is basically a chartered mechanical engineer, and he a chartered mechanical of the Institute of Measurement and Control. He was sponsored through university in Manchester, UK, by the Shell Chemical Company, and started his oil industry career with Chevron Oil, moving on to the National Iranian Oil Company in Kazakhstan, South Iran. He has held senior engineer positions in project management, design, construction, commissioning, calibration, and auditing worldwide. He has, his oil and gas metering career spans exceeds of 40 years, during which he has performed many uncertainty analyses. He started work in KOC since 2015. We may come, Mr. David, to the stage and present.
Okay. Thank you. Thank you. Actually, I started in 2005.
2005? Oh.
You said 15.
Oh, really?
Yeah, no problems. Good morning. Okay. Flow measurement uncertainty, combination of uncertainties for multi-stream metering systems. Uncertainty is basically an indication of how far from the true value your measurement is. And it's important. For a new build system, it can give you the confidence to know that your system will be accurate. And for an existing system, it can act as a health check because it embodies all the specific parts of the metering system. But there's a problem. None of the standards address the metering system as a whole. It addresses a single meter run and a meter prover. And there is no way that you can be traceable to any standard for a complete metering system. What I'm going to present here is some method of combining the uncertainty of single stream metering runs into an overall system. Okay. I was involved in the preparation of this metering standard, and during that time I put forward a solution to the API committee, which was discussed, analyzed. They didn't object to it, but I'll come on to what they did with it later. The source document for all uncertainty measurements is this document here, GCJM, which was originally called Guide to Uncertainty Measurement, the GUM standard. And that's right, basically what everybody still refers to it to. It's produced by the Bureau International de Poids de Mesure, which basically means, it's a French, means the International Office for Weights and Measures. And it's the source standard for all uncertainty measurements for everything. Now, everything is a lot. It's in the whole world. But before I go on, GCJM, the Joint Committee for the Guides in Metrology, and it's an estimate. Uncertainty calculations are done, but they are still estimates. They can never be accurate. As I say, it's an estimate of how far from the true value is a measurement of anything. However, in the oil industry, we can narrow it down to, rather than uncertainty of everything, use this standard here, which is the ISO standard, measurement of fluid flow, or the measurement of petroleum, statistical aspects of measurement and sampling, which has now been superseded by the chapter 13.3. Now, those of you who have been associated with measurement uncertainty will recognize this. It's an uncertainty budget. This one is from the API. And I draw your attention to this particular phrase here, the sensitivity coefficient. Okay, and this one is from the ISO. Again, the sensitivity coefficient. What it means is that if you have a measurement, it embodies lots of different parts. Each one will have a different influence on the total. For instance, we've talked about a meter factor. If you have a change of 1% in meter factor, that means a 1% change in the overall volume measurement. But if you have a 1% change in temperature, that will not produce a 1% change in the volume. It will produce a much lesser. By how much? By the sensitivity coefficient. This is a very nebulous, very difficult coefficient to obtain if you are doing an analysis on systems where the conditions are constantly changing. If you have a new build system where you're working basically from statistical data, then you have an uncertainty, a sensitivity coefficient, which does not change. But if you have an operational system where your temperatures, pressures, flow rates are constantly changing, then the sensitivity coefficient will also change. Now, the evaluation of uncertainty, it's necessary to combine all the uncertainties of temperature, pressure, API gravity, water in oil measurement, the meter proving, the meter factor. So there are a lot of different coefficients or different parameters which are coming together and have to be combined. And you don't know what each one will basically give you until you've examined all the parameters. You can't leave any out at all. Some are going to be more contributory than others. It's a complicated way of doing an analysis, and there's a better way. In ISO 5168, they call it the numerical solution. In the API, they also call it the numerical method. And basically, it's saying that where no mathematical relationship is available, or the functional relationship is complex, it's easier to obtain the sensitivity coefficients numerically by calculating the effect of a small change on the input on the output. Now, we know what the algorithm is for oil measurement. It's basically specified in API 12.2.2 measurement tickets, which takes the algorithm from chapter 11, and specifically 11.1.6.1, which has all the contributory factors to the oil measurement volume, temperature, pressure, API, and the water in oil. So we have an algorithm, and each of the individual components is evaluated using one of the following methods: a type A evaluation, which is a series of readings using statistical methods, or a type B, which is everything that isn't type A, basically. And we combine it into a spreadsheet where we have the process conditions here, we have the uncertainties or the errors, we have the outputs here, the effect of the outputs of each of the different parameters, and then we calculate the overall uncertainty for a single stream metering system. So for a meter uncertainty, which is the primary element, it's the major part of the contribution of the uncertainty, we use a statistical analysis. An API says, as well as the ISO, that reproducibility is the range of uncertainty at 95% confidence level for the difference between two measurements. How many measurements? It never tells us. It says, but basically, you can have 5 to 10 measurements, but it's more acceptable. The more measurements you have, the better assessment of the uncertainty you have. Now, if you have less than 25, and basically if you look at 25, normally for a 95% uncertainty, we call it 2 standard deviations. It's actually 1.96, but because it's an estimate, and GUM says we're estimating, everybody calls it, they round it up to 2 standard deviations. If you have less than 25, you have to use the student t-factors and apply those. It's getting a bit complicated, so I'll rush on through here. The meter factor uncertainty, this is one of KOC's meters, this is SIA, and the uncertainty is done from a series of proofs. So from the last 25 accepted meter proofs, we have an uncertainty of 0.036 on the actual meter factor. It's a very low value. That's because KOC are very good at blending the oil from over 2,000 wells into a very consistent oil, Kuwait export crude. So we're getting consistency day after day after day, and that gives us a very low uncertainty on the meter factor. So we've come up now with, again, this 2 standard deviations, 0.036%. That goes into the spreadsheet up here. 0.036. Over 60 proofs were done, but only the last 25 were considered. Okay, so we then go into the API 11.1.6.1 calculation, which is a spreadsheet which is validated against the 15 examples, printed examples in the API, and we can put in all the different parameters that we have. Now you'll notice we have 1 pulse, we have one as the meter factor. Why? Because we're going to do a comparison here, a relative uncertainty of the base case with no errors, followed by the maximum drift between calibrations, which will be the type A uncertainty. And we're using a rectangular probability. I won't go into the details now, but so we do a calculation of the metering system with no errors according to the API calc. We then do it for, due to the, we've skipped a couple here, there, meter pressure, meter temperature, meter pressure, API measurement of API gravity, the error due to the API gravity. And every time we're coming in with a different net standard volume. So we're getting, this is the net standard volume error due only to the API gravity measurement. This is the net standard volume produced embodying the error in the meter pressure. So for each parameter, we put in the error for the metering system. We then come on to, this one is for the compressibility of the crude oil, so FM. So again, dry volume, net standard volume. Then we have to do the meter prover. So we have a base case of the prover calculation with no errors. We then go on to error due to the temperature on the effect of the prover. The pressure due to the error on the meter proving due to pressure. The error on the meter proving due to the API gravity error. And again, the uncertainty due to the compressibility of the crude oil. So we have 2 base cases, one with a meter with no error, and then we have one with a prover with no error, plus we have all the individual errors that have been calculated. We then, to come back to here, all the standards that you see, all the errors that you see are traceable. The calculations are traceable to national standards. So for the BS&W, we use that the reproducibility of the average water content. For the API measurement, the reproducibility, again, everything traceable, and that's the important part. You must have traceability so that nobody can call into question any of the calculations. And this is the traceability of the actual model that's used for the derivation of K0, K1, K2, which is the temperature effect. The expansion effect on crude oil due to the temperature change. And for the meter prover, we use the base prover volume uncertainty of 0.03. Again, fully traceable. And then we do the calculation of the standard uncertainty, which is the net standard volume error, minus the base case with no errors, divided by the base case as a percentage. And then we have to expand that. So the expanded uncertainty is 95% confidence level. So we use the standard uncertainty multiplied by 2, which was the one we saw was 1.96, but it's rounded up, divided by a probability distribution factor. Here we have the rectangular probability, which basically means that the minute you've calibrated the instrument, it's immediately, the uncertainty on that instrument is the as-found error at the next calibration. For a series of statistical analyses, we use the Gaussian distribution. And for one what you would expect to have perhaps a gradual drift of uncertainty between the last calibration and the next calibration, where you get a gradual drift, and that's the triangular probability. You'll see that these are statistical factors. We divide the actual uncertainty by √3 here, and the actual uncertainty by √6. So √6 would give you a smaller uncertainty. So if you have any concerns, it's always best, and the standards say, to use a rectangular probability. So the triangular, this is the rectangular probability, and this is the triangular probability. So then we combine all these different errors due to the different measurements of temperature, of meter proving repeatability, the pressure, the API, BS&W. All of these are the errors that are attributed to the measurement errors due to temperature, pressure. And you'll see some of them come out to 0. If you're going to do an analysis, it can be of a new build. You have to use the manufacturer's standards or specifications, which have to account for every eventuality. Fluctuations in voltage, ambient temperatures, and because of this, their specifications are quite large, quite big. The variations are big. But if you have a system which is under statistical control, where the temperature, the pressure, the BS&W are not changing that much, which is the case here in Kuwait Oil Company, where everything's under very, very good statistical control, the actual uncertainties can cancel out. So then, and each one, as I said, is traceable. All these individual errors are traceable to different parts of standards. And then we combine them by the sum of the roots of the squares. Everything you've seen is traceable. and the uncertainties are always expressed as an absolute value. In 1998, I was given the job of doing a mass balance on the Hibernia platform, which is offshore on the east coast of Canada, to do a mass balance with associated uncertainties. And I came up with a problem because we had some very big flows with very small uncertainties and some very small flows with very big uncertainties. And if we were to use the combination of the root sum of the squares, it would not give us an accurate assessment of the uncertainty. So I went to St. John's University, Department of Mathematics and Statistics, who gave me this pooled variable principle of the way to combine multiple meter streams into one skid. This was one system, and even the statisticians couldn't agree because we got a second one from a different professor. So basically, if we look at the weighted uncertainty, it will give us slightly more error than if we had the pooled variance. Sorry, am I running out of time?
You deserve it? You're getting green on someone now.
Okay.
You deserve it.
So basically what we do is we take the uncertainty of, we have 6 meter runs on this particular skid with the individual uncertainties of each meter run. We then multiply it by the percentage of product that has flowed through those metering runs during the batch, and we come up with different values here. We sum them and divide them by 100%, and we end up with an uncertainty of the whole system of 0.064. Again, it's very low because it's under statistical control. There's also a second method we can do here. Where if you have a metering system with not just a single meter, but by combining the measurement of L meters in parallel, you can reduce the uncertainty by dividing it by the root of the sum of the numbers of meters that have been used. And then we have to add the uncertainty of the meter prover because it's fully correlated. So we had, in the case you saw before, let's just go back. These numbers here are whether or not you've got a contribution of the quantity that's gone through. And the way we did it was to say, if we have more than 15% going through a single meter stream, we can say that it was used during that batch. And if it's less than 15, it wasn't used in that batch. So in this case, we had 3 meters that were in service. So the L becomes 3. So we divide by root 3. And then we have to add the uncertainty of the meter prover, which you saw before was 0.03. Now, as I said to you before, I was... okay, this is the way we express the uncertainty. So we had the 0.067, 95% confidence level, 109 proofs. And we shouldn't give uncertainty with excessive number of digits. This is the GUM standard. It says at the most 2 significant digits. So if you see uncertainties with 4, 5, 6 decimal places, it's not significant. Okay, so I was working with the Petroleum Measurement Committee to do the compilation of the API 13.3. This procedure that you've just seen, I put to them. And they said, we have got a problem here. The parallel meter problem has not been definitively solved. Accordingly, they did not address this issue in the 13.3. So I carried on and I said, look, we've got to address this problem. And they said, well, we will do in the next revision. And they have done. In the December 2017, they addressed it by saying, although this document could be used for the analysis of an entire system facility, this standard, it's outside the scope. So there is still no definitive method of combining single stream meters runs into a skid. Not in the ISO, not in the API. We've got to address this because it is still an open question. Thank you. All right. No questions. No time. I'm sorry I overran.
We will give questions.
Oh.
Yes, of course.
Yes.
Can we give him the mic, please? Where? Oh, there you go.
Thank you for the excellent presentation. I really appreciate the great effort you did here and sharing with us your experience. As you said, uncertainty is uncertain sometimes, in fact. I see the way you calculated the uncertainty, which is totally different than most uncertainty calculated. There, they are also considering the errors of the instrument itself that came from the manufacturer for the RTDs, BTs, flow computers, and also whatever instrument is used in the calculation. What you have came up with is something depending on the calculation itself. It's not considering the errors came from the manufacturer. This is, as you said, in the gums, there is type A and type B. Type A is assuming that when we are reproducing the process, that it is exactly typical to the one before it, with the same conditions, and then you can have a reproducibility. And as you know, in Kuwait Oil Company and other and things on the sites, in the field, it will be very hard to have something exactly identical to be repeated to use this uncertainty. So my question is, this uncertainty, which came up from the manufacturer, not mentioning it in the calculation, although manufacturer is saying that, listen, our device is uncertain with this, how we are going to say that the calculated uncertainty you did is enough to cover also for such an uncertainty?
Okay. There are uncertainties in all instrumentation. Periodically, the instrumentation, let's say the secondary instrumentation of temperature and pressure, are calibrated quarterly. So, and it's done in accordance with the API 22.2, which is 22.1, which is an end-to-end calibration where we apply either the pressure to the field instrument or the temperature to the field instrument with a dry block calibrator or a pressure calibrator, and we observe the effect in the flow computer itself and vary the calibration through the zero span and offset, which basically takes out all the intermediate parts of any instrumentation uncertainty, the analog to digital conversions, the digital to analog conversions. And if the actual instruments that are used to do the calibration are of sufficient quality, which they, of course, they must be, of one order more accurate than the measurement, the instruments that they're measuring, then it increases your confidence that the manufacturer's stated uncertainties have already been calibrated out by using a secondary traceable instrument, which itself, as you know, in the temperature measurement, we don't just rely upon one temperature measurement, but we have two fully traceable reference instruments to check the referenced instruments. So we are always trying to keep ahead of the game by narrowing down the uncertainty of measurement. Of the calculations, we include, there is an uncertainty in the calculation, and we use 1 in 10,000, which is the API. So we have an uncertainty in the calculation of 0.01%. We will never get that in a 32-bit computer, but we include it because it's there in the standard. So what you've seen here basically is an estimate. That's what GUM says. It's an estimate. And we can try to reduce the errors in any estimate is impossible. But if you can reduce it to 95% uncertainty, which is the industry accepted, then we are within the tolerance that is required by the oil industry. Okay.
Thank you.
One more, please, question.
One more, okay.
One more question.
If you get me on this, I can go all day. That's a problem.
Thank you. It's just, you know, I'm so convinced about the way you calculate the uncertainty.
Yes.
In fact, I used it myself, your Excel sheet back in the company.
Yes.
And I'm so convinced the way you look at it from an engineering point of view. But also the other uncertainty way calculation has its own benefit. And I believe it's a must to be done in addition to the way you are doing it. Why? Because it will sometimes tell you where you are most uncertain in the chain, in the cycle. I'll just give one example, just for, in this case, an uncertainty done to one of our metering system. And by doing that bank for the uncertainty and putting the uncertainty of each device,
yes,
we came up, there was one analog digital converter installed to convert the analog to digital near to the flow computer, which the uncertainty of it was the most high and affected the whole uncertainty of the skid. And then we were able to just replace it with a more accurate one, which made up our measurement more accurate.
Yes.
So your uncertainty, yes, as a calculation wise, will be addressing how accurate I am, but it will not help me in the other side, which is identifying which part is most uncertain in my whole metering skid.
If I get you right, you're trying to identify which is the component which is giving you the most uncertainty.
Yes, the way you said your uncertainty, calculation-wise, is excellent.
Yes.
From engineering point of view, I totally agree with you. But the other way of calculating the uncertainty with the banks, identifying the manufacturer error of each instrument,
yes,
putting it beside together, will give you the chance to know which instrument exactly has an high uncertainty, such that you can go ahead and improve it, replace it with a more accurate one.
Well, using the numerical approach will give you that automatically because you put in the actual uncertainty found during calibration, which is, as I said, the end-to-end calibration. We're not doing a component calibration of, let's say, the pressure cell or the A to D, or we're applying pressure from a calibrated instrument, and we're seeing the effect at the flow computer. And the flow computer value displayed should be the value that is used in the calculation. And if there is any error in the pressure or the temperature, then that can be removed at the flow computer by the zero span and offset, so that we are trying to come as close to the true value as possible. If there's an error in the calibration instrument itself, yes, that's a problem. But pressure is not so important, as we know, on the compressibility of oil. But temperature is important, which is why KOC bought 3 traceable independent probes to be sure that the instrument we're using at the calibration is as accurate as it possibly can be. Okay.
Thank you, Dave.
Thank you.
And if you have any question, you can ask him during the lunchtime, but don't know him too much. Let's enjoy the break.
Oh. Thank you very much.
Thank you.
Thank you. Ooh. Okay.
Thank you, Maher. Thank you, David. Our next speaker is Mr. Ninan Matthews, an engineer, management professional, currently working with Emerson Automation Solution as a senior business development manager for Roxar production for 9 years. Total industrial experience is 17 years, and worked with oil and gas operation and EPC contractors in Middle East and Africa region. Area of expertise is mainly on reservoir monitoring, a multi-phase flow meter, production optimization in oil and gas industry. Mr. Ninan, you have 15 minutes.
Thank you.
The stage is yours.
Morning, everybody. So we already talked about single-phase flow metering, uncertainties of measurement, ship loading, etc. My topic is three-phase flow measurement. So the keywords which I want to discuss is non-gamma and wellhead measurement. Non-gamma because traditionally the multi-phase flow meters that are used by operators are based on a radioactive technology, and that requires some import license. The country needs to allow you to import radioactive source, and sometimes operators in the field are also concerned about HSE for their health and issues. They don't want to work around a radioactive source. So many operators like KOC prefer to use a non-radioactive based multi-phase flow meter. When you say multi-phase flow meter, it's handling three phases that you are producing from a well, which is a combination of oil, water, and gas. Now, the second point which I want to discuss is wellhead measurement. Wellhead measurement means metering directly on the wellhead, which is not the traditional way. So what we did as a vendor, we went and checked with operators, why are you not using meters directly on wellhead? Why are you using quite downstream on a manifold or in a gathering center? Why not directly on the wellhead? So we asked the challenges the operator has, and based on those challenges, we as a technology provider is trying to offer good solutions that operator can benefit out. Secondly, the point is multi-phase flow meter, unlike a single-phase flow meter which require extreme accuracy and measurement uncertainties, multi-phase flow meter is not a flow measurement device alone. It not only gives you flow measurement of what you are producing from a well, it also helps to optimize your reservoir production or well production. It helps you to manage your reservoir better. So unless you have measurement available, you cannot make intelligent decisions, right? And also we all know that the fields are getting mature, reservoirs are depleting, water production is increasing. Nobody wants to have water producing from an expensive well, right? Water is considered as evil in oil and gas industry. The aim is to optimize the production of gas and oil and reduce the production of water so that you can avoid the cost and operational cost involved with water handling once it brings to surface. So when we asked the operator, these are the challenges so operators has mentioned. We did some survey in various operators. So one of their comment was, the multi-phase flow meters are too expensive to put on wellhead. We cannot afford to put 1 meter per well. So that was one of the challenges. The second challenge was, okay, I want a cost-effective technology, but I don't want to sacrifice the quality of data. I need still good quality data so I can make intelligent decisions. So cost effectiveness is required, but they don't want to sacrifice the quality of data. And also with the data, he want to basically maximize the field revenue, he wants to increase the production or optimize the production from the wells. The third challenge is, that in a field, we have variety of wells. Some of them are very low producing wells, some of them are very high producing, some are old wells, some are worked over wells, some are even wet gas wells. So you cannot have one technology that covers the full range. You can have it, but it's going to be too expensive. So based on his needs, and sometimes, the well, when you drill a brand new well, you may be producing maximum oil, but over a period of time, the production matures, you start producing more water. So based on his needs, he wants to use a technology. So this is the basic important challenges the operator mentioned, and this is the solution that we are trying to offer as a technology provider. So traditional way, like I said, you have multiple wells coming from the reservoir, it goes to production manifold and various stages of separation, while you have a test manifold or a remote header manifold in the field, where you are bringing either a mobile separator or a multi-phase flow meter. Either it is permanently installed or you are using it well testing. I mean, you are testing one well at a time. The challenge there is the separators are very huge. It's not easy to reach the remote locations. Sometimes, the number of well tests that you can do is limited. By having a multi-phase flow meter permanently in the field to replace this huge separator, you are able to do more well testing, but still it is based on a testing schedule. The operator will tell, okay, this is the well I want to test today, and then he go to the next well. So again, you can reduce the cost a little bit, but not significantly. The quality of data received is still intermittent. Only you get the data from the well when you test it. What we are talking here today is, and obviously the multi-phase flow meter that you see here today is considered too expensive to be installed on every single well. So the solution that we are offering is 1 meter per well. By having a meter per well, all those challenges are taken care. We have introduced technologies that can be extremely cost effective, that you can put it directly on wellhead. So you get individual wellhead metering. Second challenge we discussed is quality of data. By using the fault-proven technology, field-proven technology, we can still get good quality data so you can make intelligent decisions. And by having a modular technology that you can adapt to your requirement, we will see that. So this is the solution which we want to discuss and present with the team here. Existing fields. On a green field, you can put, the field is still being constructed, your pipelines are still being laid, you can put meters. But there are already brown fields available where you have test manifolds available. Still, you can adapt the individual wellhead metering just by making some small modification on the wellhead pipelines. Right, so first challenge, cost. How we are able to bring down the cost on the meter is by using a proven technology which basically try to reduce and meet the operator requirements. Traditionally, meters are designed for very high pressure. So based on your wellhead requirement, we are designing meter low pressure design, because the meters is normally made of inconel because of H2S in the field. And by reducing the design pressure, we can bring down the material involved and thereby bring down the cost. So that's one step. Non-gamma, like I said, radioactive source involved operators are concerned and worried about their health and safety. Employee unions do not want to work in fields where there is radioactive source involved. So we are able to bring down or bring in a technology which can have both radioactive and non-radioactive options. And by having a compact and lightweight solution, again, the cost is reduced. It's quite easy to install directly on the wellhead, and you can run it using even solar-powered meters. And the second challenge was the second challenge was cost is reduced, but still you don't want to sacrifice the data quality. So by having a field-proven technology and by having advanced signal processing available on the softwares and the flow computers, as well as with limited input data requirements and the non-gamma, non-radioactive version, and having a meter on the wellhead will give you immediate changes happening in the well. In a traditional well test, you will get to know only changes when you test the well. But having a meter directly on the wellhead, you are getting immediate changes in the well. By having immediate changes happening in the well, you are able to make intelligent decisions to choke down the production or to increase the production, etc. Then again, the next one is about the flexibility. Like I said, variety of wells are there. Some are low producing, some are high producing, some are gas wells, some are critical wells for the operator to continuously monitor. So based on your requirement, we can add and remove the modules from the meter. Having the radioactive source or not having the radioactive source. Having the Venturi section or not having the Venturi section. You need extreme accuracy, you add more modules. By having less modules, you get slightly uncertainty results, but still you get a reading from the wellhead. At least you know what is the changes happening in the reservoir. So and again, by having the modules, you can extend the life of the meter also. For example, the meters are designed for certain production today. Maybe your well is producing 6,000, 7,000 barrels. But next, over a period of 10 or 15 years, the production is going to deplete. So that means you need to invest again to buy an inconal meter, expensive meter. But in case of new technologies right now available, you don't need to change the complete meter as it is. You can remove the Venturi section from the meter, and you can put a new Venturi with a smaller throat, and this way you are able to continue using the same meter. So this is again the flexibility available. Like I said, field mature, the wells can become a wet gas well. By adding the wet gas module, you can continue using the meter. So a modular solution is available now. Now coming to non-gamma, which is especially interesting topic for Kuwait, because here employee unions are there who do not want to work with radioactive source in the field. So we have a mature technology now available with non-gamma version. So by having a non-radioactive technology, you can avoid all the import-export paperwork required to bring in the radioactive source. It is quite easy to deploy and operate standard meter. The only difference is meter is not without a radioactive source. No more operator concerns because field operators are concerned about their health and safety, but here there is no radioactive source involved, so it's a field-proven technology. We have a large install base of non-radioactive meters in the Middle East. Various operators are already qualified and using the meters on individual well metering. It still cover, okay, you are removing a direct measurement from the meter by removing the radioactive source, but still it cover the full range and it is tested and field-proven as I mentioned. So this is basically showing the different modules available from Emerson. As you can see here, this was the standard multi-phase flow meter, the 5000 psi design pressure rated. It's extremely expensive and it is having a lot of inconal material involved because it is high design pressure. But you can see here these meters are still available with radioactive source and without radioactive source. That means the radioactive source is available as a module which can be retrofitted onto the non-gamma meter. Then still you have the same versions available, but this is with less design pressure. It is 3400 design pressure options. Now you can see here on this meter there is a Venturi section. You can remove that Venturi section just by having the electrode part. You are still able to measure wellhead measurement. That way the meter become very cost effective, but the uncertainty of measurement is slightly high in this case. So this way you are able to still get three-phase flow measurement. So we already discussed this. Just to give you a last slide here, a cost comparison, because operators are not very sure whether putting a meter on a well is really cost effective or not. So this was a study done by one of the operators in Middle East where they had 3 platforms offshore. Each platform had about 10 producing wells. They did a cost comparison of the conventional manifold or well testing using 1 meter versus putting meter on every single well. Over a period of 30 years, because when you are investing some money, you need to look at how the investment will make you, so they use this net present value, NPV calculation.
3 minutes, please.
Right. NPV value, and you can see here the calculation based on this were the criteria they used, and availability around 95% for continuous monitoring basically. And based on, you can see here, the capex involved was around $8.9 million, while using individual meter, you can avoid all the testing manifolds, valves, diversion valves, all infrastructure you can reduce. So the cost saving itself is significant, comparable. And also over a period of 30 years, you can see the net present value calculated for individual well metering is also quite cheaper compared to the conventional. On top of that, you can see by having a meter available on wellheads, you are getting continuous data. So there is a value for the data, and with the data, you can enhance your production, you can optimize the reservoir, you can manage the reservoir better. So these are additional benefits. And also by having individual well metering, you are able to enhance the production of your wells, as well as you are able to better manage your reservoirs. So that was a brief introduction to the modular technology and individual well metering. Operators, to conclude that operators are these days looking at having technology available directly on wellhead. We talk about digital oil field. Having a technology or measurement directly available on wellhead, you are able to get better data and better manage your reservoir.
Thank you, Mr. Ninan. Any question?
Thank you for your presentation. I didn't get the, how did you, you said it's cost effective, and I really didn't get, for example, for the last slide, you showed the study of I don't think it will affect the reservoir management or enhance recovery, because at the end of the day, in any meter, you should see how much gas or oil coming out of the reservoir. I don't think that it will really improve. The second part of my question is, did you consider the OPEX? The OPEX will be higher.
That's correct. That's correct. If you see the last slide, it was considering the both CapEx and OPEX over a period of time. Even if you have conventional manifolds, you still have valves. You still have, if it is a remotely operated valves, you still have a chance of it getting failed, and it require some operator or a maintenance intervention periodically. By removing the manifold, you are left with only one equipment which requires some maintenance or calibration, which is the multi-phase flow meter on each well. But as I mentioned, that we have, when that study was done, they have considered both CapEx and OPEX. Multi-phase flow meters, yes, if it is a radioactive source, you need some periodic calibration. But when you are removing a radioactive source, you don't need any more calibration. Maybe once in a year, you need to send a technical guy or a service engineer just to help check the meter, make sure the input is correct, your composition has not changed. That's it. So once in a year intervention is all you need for a multi-phase flow meter. So the OPEX is also quite less compared to conventional manifold system. First point, I didn't get it clearly. You're saying that not having a measurement?
You said the multi-phase flow, you said there is, one of the challenges is the cost, right?
Yes.
I didn't get the point. How did you overcome that?
I got you. Good question. So basically the modules you see, the base module is only available with electrodes. That means you are avoiding the venturi, the transmitter, you are avoiding the whole inconel material from there. So thereby you are able to bring down the cost. Then I show you the difference between the 5000 psi design pressure versus the 3400 psi, because many of the wellheads, you are installing the meter after the choke valve, where the pressure is already reduced, right? So you don't need a 5000 psi meter for every application. You can use a low pressure version, which is suitable for your well, and you can thereby bring down the cost.
Of course, if you reduce the pressure, the features of the flow meter will be reduced, means the cost will be reduced. I don't see any. Anyway, another question. Is it used anywhere in our NOCs and IOCs, and for example GCCs or GCC countries?
Then,
please?
Right.
Any experience?
The base, thank you. The base version of the meter without electrodes, which I show you in the left-hand side, that's not yet used. We are still looking for opportunities to field trial. But the low pressure version with gamma and without gamma, it's been approved by Saudi Aramco. Even it is being used in Kuwait for your projects here, the non-gamma version, low pressure version. And Aramco is putting 1 meter per well. So they are using the non-gamma version, low pressure version for maybe 250 to 700 wells already since last 3 years. It was qualified for Emerson, it was qualified in 2013, the non-radioactive meter with low pressure version.
Thank you, Mr. Ninant. If there is any more question, Mr. Ninant will be available during the day. Thank you so much.
Yeah, thank you.
Our next present with Maha. But before that, can I call Mr. Javin Monroe? Is he around? Okay.
Hello. We're almost to the end of the session, so 2 more to go. Bear with us. For the next session is going to be about measures towards accurate flow measurement selection that will be presented by Mr. Yasser. Yasser, he's a certified professional engineer in automation and control by Engineering Australia. He is also a TUV functional safety engineer and credential in electronics and controlling engineer by West Canada and Mansouriya University in Egypt. He has 20 years of experience in oil and gas and petrochemical industries. He joined KOC since 2007. You may come. Thanks.
Assalamu alaikum. Good morning, everyone. Thank you so much for having me, and I'm very delighted and honored to be here today. I stand today before you to talk about flow measurement selection. And these are the topics that I'm going to cover, hopefully, during my presentation. And honestly, I would like to pass 2 messages to all of you regarding this presentation. First of all, we have to feel the importance of flow measurement selection, because most of the time we are just following just cliches. By whenever there's a flow measurement requirement, we put orifice. Whenever it's a metering, we just put turbine. I just need to get rid ourselves of these cliches and stereotypes. The second thing, I'm going to give you some techniques about flow measurement selection that would help you narrow your choice in this topic. So let's get started. Selection in general is tough, and this is one of the most challenging thing I've ever faced in my experience, in my 20 years experience. So selection is tough, but it's even more challenging if you have a wide variety of choices. If your choice is amongst a wide variety of things, this is going to be very challenging. On top of that, it's going to be even more challenging if the thing that you're choosing is so critical. And this is exactly the case when it comes to flow measurement selection. So from the wide point of view, it's ridiculously wide, honestly. Each and every technology flow measurement selection can even further subdivide it into subcategories and subdivision and sub-technologies. For example, if you had a head type flow meter, which is a very, very big family, you can even further divide this into Venturi, orifice plate, pitot tube, and so on. When you go further, you can even, each and every design of this can even further divide it into further divisions. Like, for example, if it's an orifice, what kind of orifice? Is it sharp edge? Is it conical entrance? Is it quadrant edge? And so on. For ultrasonic, is it Doppler? Is it transit time? And so on. So this is for the wide variety of, this is the first challenge of choosing the flow measurement. This is just a simple example that shows you how wide is the variety of the flow measurement. The second challenge you might face in choosing the flow measurement, the right flow meter, is the criticality. The criticality of flow measurement selection is not only because it's linked with money by selling and buying the products. It is also critical because the error of incorrect reading flow measurement, it can vary from a minor flow measurement reading to maybe some process upset. It can move you up to catastrophic events and even some fatalities if you're not properly selecting the meter in the right application. So in order for you to feel how critical is the flow measurement selection in our facilities, this is just a quick example. Suppose you have a facility that produces 300,000 barrels oil per day, and you have a metering system that is measuring with an accuracy 5% of full scale. Then the error will be up to around 15,000 barrels per day. This if you just calculate this for a range of $70 per barrel, then you are losing around $1 million every single day. Can you imagine? $1 million just because of 5% inaccurate meter. So one of you might stop me now and say, hang on a minute, Yasser, this is not realistic. This 5% is no more there. We have a very advanced meters now out there, and we have 0.1%. Yes, if it's properly selected. If you have properly selected the meter in the right application, yes, you can achieve this accuracy, but this is very, very optimistic. If you have wrongly selected the meter, you might even get worse than that, and sometimes the meter might not even read at all. So this is the first example. Second example, we have to think, especially when we use this head-type flow measurement, which is altering the pressure, which is dropping the pressure to measure the volumetric flow. We have to think that this pressure that you're dropping is just money, is just energy. In order for you to raise this pump, you are buying a compressor or a pump and paying for it for energy. So this is just a calculation. I can explain it further during the break if you wish. But in order to work this out, this is just a small example. You have a 16-inch line with a flow of around 1,000 gallons per minute. This is just the water. And you will choose an orifice, normal orifice, with a delta P, which is just 250 millibars, 3.6 psi. It's very, very small amount of pressure drop in order for you to calculate. Can you imagine how much energy you are losing every single year just because of this orifice? If you work this out, it will end up around $11,500. $11,500 just the cost of the energy you have already paid for the compressor or for the pump in order for you to get this meter measured flow. So you can multiply this by the number of orifice plates you have in the facility. And so you have to think many times before choosing each and every meter. It's not a matter of inserting orifice as a cliche in each and every flow measurement application. So it's not a matter only of capital cost. There's also installation cost, operation cost, and running cost. So this is the second. Traditionally, when we go for selecting the flow measurement, we go through 3 steps. The first step is the suitability. And in suitability, my advice, we put all the required data in a form of data sheet where we put the instrumentation, process, mechanical, and electrical requirements. For example, the instrumentation, you have to see the functional requirement, like whether it is going to be for monitoring, for control, or for safety, for tripping or something. The other thing for process, you have to put all the process conditions that are available. And you have to see whether you have a meter that can meet this requirement or not. For example, the pressure, temperature, viscosity, density, compressibility factors. All these factors are required as a process. Then the mechanical, you have to see whether this meter is going to be connected to the process by a flange or threaded or welded. What kind of welding? Is it butt welding, socket welding? Is it threaded, metric, or NPT? If it is flanged, is it flange face, raised face, flat face, or ring type joint? All these things, does it require an external power supply or not? All these figures in the first step, when you gather, in this step, you just, after you get this all data, you just go to the sample of selection tables. These selection tables, this is just a sample of selection tables. There are so many of these examples out there on the internet and on the handbooks. So this can help you easily narrow the choice between, for example, 30 technologies to like 10, 15 technologies. These examples I can explain further during the break if you wish, but this is showing for example, this is, for example, telling you this, for example, this turbine, what kind of application can be used, whether it is correct, whether it's fine or not suitable, or sometimes you'll find SD, which is like special design. So this is just an example of the selection table. Then you move to the second step, which is the performance. In performance, there are 2-3 points I need to emphasize. First of all, you should not go and say, I need a meter which is 0.00% like this. First of all, you have to understand the manufacturer when he tells the accuracy of what. Is it for actual reading or full scale or for the scan? Second thing, you have to tell yourself, you have to choose a realistic error that you can accept, tolerable error. So first of all, you choose the error which is tolerable for you, realistically, not imaginary. Then, after that, you have to choose the rangeability. You know why? Because the rangeability is affecting much the error. The wider the rangeability, the bigger the error. So don't go for a bigger rangeability if you don't really need it. So this is the second thing. After you get this rangeability and error together, then only you can decide the range of the meter. So this is also very, very important. Then the third step, the third and last step is and this step is optional actually. If you have any special application, because special application requires special design. Special application like pulsation, like hammering, like very viscous, if you have slurries, if you have very high temperature like steam, if you have very low temperature like cryogenic, all these special conditions require special designs. When you finish all these steps, traditionally, this is our traditional approach. So is that enough? Of course not, because experience matters. How experience matters? You can do all these steps, but I cannot guarantee that you would reach the right meter in the right application. So what to do? I'll give you just an example to let you know how experience is important. Do we have a magnetic flow meter in the market that can measure up to 500,000 gallons per minute? Yes, the answer is yes. Do we have a magnetic flow meter in the market that can measure at a process condition of 1,500 psi's? The answer is yes. Okay, I need a magnetic flow meter that measures 500,000 gallons per minute at 1,500 psi. Not available. This is available in its own, this is available in its own, but together they are not available in the market. No selection table will tell you that. You will get this only by the experience. So this is the second thing. So experience matters. The second thing is the complexity. The higher the complexity, the easier the choice. For example, if you have a complex application like high corrosive, non-conductive sludge, the selection is going to be very, very easy because it's going to be like ultrasonic cross correlation. But if you have a straightforward water application like that, you'll find that most of the flow measurements are applicable, and at that time the selection is going to be very challenging. Ever since Bernoulli established his theory, 1883, that governs the relation between static head, elevation head, and viscosity and velocity head, static head, and elevation head, we have derived this golden formula. This golden formula is showing that the volumetric flow rate is a function of the differential pressure across any orifice or any head type flow meter. So simply most of the manufacturers, they have manufactured in that manner. We need a differential pressure transmitter. When we measure this, we do some algorithm, then we get the volumetric flow rate. And this was the impression, and this is applicable in most of the flow meters. But actually, in practical life, there are two factors that would affect this formula. First of all, the velocity head. This velocity head is easy to calculate. It's just square the velocity over the twice of the acceleration, gravitational acceleration. You can simply calculate this. For example, if you have a 10 feet per second velocity, the calculation there, it would be 1.5 feet. This is the velocity head. If it's 3 meters per second, the velocity head would be like 0.46 meter. This is the velocity head. How this velocity head be affecting on my selection? This is an example. For example, you have to keep in mind that orifice plate, for example, requires minimum 4 velocity heads. Means that in this example, if I have 10 meter per second velocity, which is 1.5 velocity head, then at least you need a 6 feet as a velocity head, which is going to be a permanent pressure loss. If you don't afford this pressure to lose, then don't go for orifice. You have to go for vortex or some other technology which is consuming lesser velocity head. I'm just moving fast because I have only 15 minutes, I guess, or 20 minutes. The second thing is the Reynolds number. I don't want to go technically to explain what Reynolds number is, but I believe that most of you guys know it. So Reynolds number is just a ratio between the forces that help the flow the media to flow over the forces that prevents it from flowing. So it's the inertial forces over the viscosity forces, like you can say that. So this is the formula of it. It's video rho by mu. It's very simple even to remember and easy to calculate. What is the importance of Reynolds number? The importance of Reynolds number is in this formula. Theoretically, I have to only measure the differential pressure, and from the variation of the differential pressure I'm measuring, I should only calculate the volumetric flow rate. But practically, this constant, which we call discharge coefficient, it is not really constant. In many of the head type, in many of the measurement technologies, this constant is not really constant. It varies drastically with the Reynolds number variation. So now there is a tricky point. Then I have to watch, I have to keep my eyes open for the variation of Reynolds number and see how it's going to affect my flow measurement. So this is the situation. Okay. So what should I do? You should do, whenever you do any selection, first of all, measure the Reynolds number at the minimum flow, measure it again at the maximum flow, see the variation, then come to such graphs like this. We have so many other graphs like this out there on the market. Then you can see the variation. This graph shows the relation between Reynolds number variation and the discharge coefficient, which was supposed to be, 1 minute, okay, which was supposed to be constant. But as you see, it's not constant at all. So see, it's variating with the Reynolds number. For example, just give me 2 minutes, if you don't mind, just 2 minutes. So as you see here, this is the concentric type square edge, which is the common used orifice type that we're using. See how big it's variating with the Reynolds number. As you can see here, the Reynolds number starts to be steady from this point, which is around 20,000, which means that, rule of thumb, don't use orifice meter as long as the Reynolds number is less than 20,000. Less than 20,000 Reynolds number, don't use it. Second thing, if I have this case, if you have an application which is having Reynolds number less than 20,000, then I have to do one of two things. Either to change the design of the orifice itself, by moving the orifice square edge and use quadrant edge or a conical entrance, or I can even change the design and go to some other technology like magnetic flow meter, which as you can see here, it's just a steady horizontal line that has no impact or is not being affected by Reynolds number at all. So this is also one of the examples. So in general, so here's, for example, some designs. This is the conical entrance. This is the quadrant edge. Just a variation in the orifice can help you work at lower Reynolds number and lower beta ratios. So here's a table. Here's a table that can show you that the conical entrance, for example, as a design, can work for beta ratios from 0.1 up to 0.0 number. You can go for the quadrant edge from 0.25 beta up to 0.6 beta ratio. It can go up to 3,000, 300. All these are very, very low Reynolds number. So like that, this shows you how Reynolds number and how velocity heads are affecting my selection. I should not go as a stereotype and copy orifice everywhere and turbine everywhere whenever there's a metering like that. So this is just, I'm now concluding very quickly in a minute. So this is just a common mistake that we used to see. We are putting orifice everywhere. For example, the multi-phase flow meter. Yeah, for multi-phase flow meter, there is a point. I've seen some applications, they are trying to use it as a metering. Multi-phase flow meter, yes, it can measure multi-phases, but it's not for metering. We can use it just to know how much gas, how much water, and how much oil, but not as a metering between two facilities disputing. The second thing, the only meter in the world that measures the multi-phase is the multi-phase. Other than that are just measuring either volumetric or mass. And 99% of the meters in the market are just measuring volumetric flow rate. The only few technologies that measures mass is the thermal mass and Coriolis and similar things. The other thing that using Doppler type ultrasonic flow meter in a clean application is wrong. It's not. It's going to give you inaccurate reading. Transit time in a dirty application is also going to give you inaccurate reading. For example, magnetic flow meter should be used for electrically conducting fluids, but using magnetic flow meter in a gas application, it would never read. Vortex flow meter, for example, it requires minimum velocity because it creates this sort of Van Karman theory, if you remember. So this vortex flow meter requires at least 1 feet per second. 1 feet per second as a velocity for liquid application and minimum 20 feet per second for gas. Lesser than that, the vortex is not going to read at all. Also, vortex requires a minimum Reynolds number. For example, less than 8,000 Reynolds number, vortex is not going to read. You have to have at least bigger than 20,000 Reynolds number for the smaller sizes like 4 inches and below, and you have to have it also bigger than 40,000 Reynolds number for 4 inches and above. This is just all from my side. I have so many things to explain further. If you wish, I'm available in the break. You can ask anytime. Thank you so much. If you have any question.
Thank you, Yasser. So we can take one question, if anyone has. No? All right. Thank you, Yasser.
Welcome. Okay. Thank you.
All right. I will transfer to my colleague, Mr. Khalid, for the last one.
Thank you, Maha. Our last speaker is Mr. Javin Monroe. Javi Moreau is the founder and managing director of GM Flow Measurement Services Limited. He started his career in flow measurement with Halliburton, going through several mergers and acquisitions until finally become a global technical advisor for Cameron's flow measurement division. He left in 2014 to form GM Flow and has taken 3 years to develop and test a Gesta cone for gas flow measurement. Mr. Giovanni, the stage is yours. You have 15 minutes.
Okay, today I'm going to talk about our laboratory and field experience of an adjustable differential pressure cone meter. Users told us that they wanted to have zero gas releases during their operation. They wanted a meter that was accurate, no intervention or zero intervention. They wanted something that was low maintenance, and they wanted something that was inspectable or repairable. If we look at, for example, an orifice plate, this is primarily for well testing operations. An orifice plate would be typically have a turn down ratio of about 3 or 4 to 1. If we look at a standard DP cone meter, we can see that it would have a turn down ratio equivalent to about 3 or 4 orifice plates. So one DP cone meter, one standard DP cone meter would be about equivalent to 3 to 4 plate changes. So we came along and we decided, could we use a DP cone meter and could we somehow merge two devices into one? So could we somehow make this 10 to 1 turn down ratio into a much wider flow range? So we had to think about a mechanism, we had to think about seals, and we had to think about sizing software to be able to do this. And basically what we tried to do is, well, what we tried to come up with is a device which merges 2 standard cone meters into one device. And what that does, it achieves this through a sliding sleeve mechanism. And the sleeve can be in 2 different positions, either in the high range as shown here. And when it's in the high range, the flow will pass through the meter, pass around the cone section and produce a differential pressure, which is simple to understand. If, for example, the flow range then drops off, for example, comparing a high flow range with a low flow range, or a high well with a low well, or a new well with a depleted well, the differential of the flow range will drop, and of course the DP will disappear. It'll be very hard to then read. So what we do is we move this moving sleeve, this slidable sleeve, into the low range position. And what that does is, of course, the flow then passes through a much smaller area, and it produces a readable differential pressure again. So by allowing this sleeve to move backwards and forwards, we've now given ourselves a much wider flow range for a specific type of, for the differential pressure meter. If we look at the flow ranges for this device, we can see that the red section here, which I believe might have a... So the red section here is the operating envelope for the high range, and the green section is the operating envelope for the low range. If we overlap the two, we can see that from the high range over here to the low range over here, we have around about a 250 to 1 turn down ratio. So compare that with a 10 to 1 for a standard cone, or a 3 or 4 to 1 for an orifice plate. For those of you who like to, some people like equations, some people don't like equations, but this is the equations for the high range beta and the low range beta. In the low range position, we have to consider the diameter of the sleeve and the cone, and in the high range position, we have to consider the diameter of the pipe and the cone. to give us the two different beta ratios and therefore the two different coefficients of discharge and then the flow ranges. This is a 4-inch meter being calibrated at NEL in Scotland. And we dry calibrated this meter with nitrogen gas. And then just for comparison, we then performed wet gas testing just afterwards with oil to see what effect the oil would have. We tested it 10 bar and 62 bar. And for this particular meter, it had a 0.45 beta and a 0.7 beta ranges, and with automatic adjustment between the two of them. These are the calibration data results for it. This shows Reynolds number along the bottom and coefficient of discharge for the high range meter and the low range meter. So you can see that the low range gives us a significant improvement where we're going down to roughly 600,000 Reynolds number here. We can go down to about 100,000 or 200,000 Reynolds number with the low range device, and that significantly increases the range. If we look at the data from those tests, we can see that from 0.45 to 0.7, 10 and 61 bar operating pressure, the minimum and maximum flow ranges that we achieved in this case was 54.5 to 1 turn-down ratio, and that was limited by the calibration facility and not by the device itself. And these were within roughly 0.5 to 0.6 uncertainty levels. When we've completed the dry gas testing, we then went on to do some wet gas testing. And we just simply repeated the same tests with additional liquids in, and this graph shows where we were looking, where the wetness ratio, or where the liquid loading was to be found. So some results for the wet gas. This is the wet gas overread for each of the high ranges and low ranges, and low pressure and high pressure. So you can see that going with the, some bits missing, oops, there we go. So top two charts are for 62 bar, bottom two charts, top two charts are for 0.7 beta, bottom two charts are 0.45 beta. And you can see that there's a spread depending on the Lockhart-Martinelli number, and also depending on the pressure rating or the pressure at the time. Generally, we see that the 0.7 beta is less affected at high pressure than it is at low pressure, and similarly the 0.45 beta is less affected at high pressure than it is at low pressure. And if we compare the 0.7 and 0.45, we can see that the 0.7 is generally less affected, the 0.7 is more affected than the 0.45 beta. So if we just look at one of those examples here, this is the 0.7 beta at 62 bar, we can see that roughly a 0.12 Lockhart-Martinelli figure is roughly represented by about 85 barrels per million standard cubic feet. So that's about the liquid loading that they were seeing on there. This is the meter in practice in the field. This is in Oman, working for a well testing company in Oman, and this proved that the meter would be operational, it would be safe to use, and it would be easy to use. During that time, we were comparing the cone meter with the existing orifice plates. So the yellow line here represents the readings from the orifice plates, and the green line represents the reading from the adjustable cone meter. And we can see during this period of time an overall difference of about 0.5%, which in customers' terms he was happy with that. He was quite happy with that. In this couple of sections here, we see 0.25 and 0.08% difference, and that we were extremely happy with that, as was the customer. The yellow section here, where the lines start to deviate a little bit, those were down to water buildup in the impulse tubes on the orifice plate. As soon as we bled off the water in the impulse tubes on one side, the two readings came back and were immediately very, very equal to each other. One thing that the flow meter demonstrated was around about 2 hours was wasted each time they started to do a well test, waiting for the flow to stabilize before they could drop an orifice plate in order to start measurement. Immediately they opened the well up, our meter was able to start reading straight away. Oops. A second well that we tested, this was a well flowing to a flare at 100 psi, and we see in this first section here the two were reading within 0.13%. So the orifice plate and the adjuster cone was reading within 0.13%, and the flow was quite stable. It was reasonably okay. The second section here, the well starts to slug. So the well's slugging on and off, and all the time during that section, we were reading about 2.7% difference between the two devices, and we start to figure out what's actually happening here, what's causing those differences. If we look specifically at the DP during that time, we see that the orifice plate is running between 30 and 60% of its range up until a point about here. Once the well starts to slug, then the DP on the orifice plate is very regularly going over 60% and very regularly going under 30%. In fact, it was about 90% of the time the DP was actually out of range. That would explain the reason why there was 2.7% difference, because we were able to use the full 400-inch range of the DP device with the adjustable cone meter, and so we were able to measure much more accurately. So, some of the conclusions that we drew. Each orifice plate has got a limited flow range, as we know. Each time we make a plate change, there's hazardous gas releases, and if there's H2S present, then it becomes very different, very dangerous. It's a hands-on device, of course. You have to physically make some changes to the plate, and it's manual. People have to do to operate it. We have to wait for stabilized flow each time a plate is changed. And of course, there is also the question about which plate do we use? A 2-inch, 1.5, 1.75, maybe have a couple of different attempts to get the right one before we see a good measurement. With an adjustable cone meter, roughly one meter is equivalent to roughly 27 orifice plates with a 250-to-1 turn-in ratio. There's no gas releases during its operation. It's completely automatic. It's a hands-off device. People don't have to touch it. Totally automatic, and we don't require to have stabilized flow before starting to measure. And we figure it saves about 60 to 90 minutes per plate size per well test. So if you have several plate changes during a well test, then you can start to save some significant time during the total test. Some future work that we're looking at, the 4-inch field trials in Oman are complete now. We want to go back and do some more detailed analysis on the wet gas measurements that we've done. We're going to run field trials in Saudi Arabia with wet gas meters for Aramco. And we want to compare CFD work that we've done with the actual well test results, and also with the calibration data. And we're just about to test a 3-inch meter in the next couple of months, and we're looking to build a 6-inch meter soon as well. So that concludes. Hopefully I'm not, I'm 5 minutes early, so everybody will be quite happy, I hope. And if you have any questions, I'll be glad to.
Thank you, Mr. Javin. We will take one question, please.
Thank you so much. It's a new design, it seems to be interesting, but it seems to be limited only for clean applications because of this intrusion that I see inside the pipe and because of this mechanism of sliding the sleeve back and forth and also the chance that this sleeve might get stuck if I have any viscous or dirty application. So it seems that this application should be only limited for clean application or even gas. Is that correct? Or?
Not really. We've done a lot of the design on the sealing mechanism. The internal bore is very carefully controlled, and it's also plated. We electroplate the internal bore, so it's like a piston on a mechanical digger. So the piston on a mechanical digger goes through all sorts of dirty operations during its life. It's moving sand and dirt and stuff. So we use the same technology that is used on those pistons on the sleeve itself. So we consider dirt, we consider sand, we consider rust, we consider corrosive fluids, and also the fact that the equipment gets moved around when it gets loaded on the floor or on the deck. Rust will come off the roof of the separator, stuff like that. So we've considered those in the seal design.
Okay, having also this design considering 2 beta ratios, having this design considering 2 beta ratios like 0.7
Yes.
and 0.45, this is okay. It gives the feeling as if you have two options for the orifice plate sizing. But from the electronic transmitter side, you have to choose the differential pressure, the different pressure across the meter to be a wider range. And this wide range, meter range, it might have impact on the accuracy as well. Because you have to get a meter that measures maybe not only 250 millibar, you have to go maybe to 500 millibar or maybe more. So when you get the wide range of the electronic transmitter, the accuracy at the lower range it might be affected. Is that
yeah? What we do is we calibrate the differential pressure device. Obviously, we calibrate the flow meter itself as well. And we have the operating envelopes are overlapping. So if you notice on one of the 2 envelopes are overlapping, so that as we're coming down in flow range in the high range, when we get towards the bottom of the high range, the low range then kicks into gear, if you like, and takes over from there. So we have that overlapping range that allows us to effectively ignore the inaccuracy on the bottom of the high range, which is then picked up by the low range.
Okay, thank you.
Does that answer your question?
Yeah, thank you.
Thank you, Mr. Javin. Mr. Javin will be available during the day if there is any questions remain. Thank you so much. Before the lunch break, we would like to call Mr. Rashid Al-Mirri again, please. And we would like to honor 2 technical committee members, Mr. Ghazi Al-Asaimi. And Mr. Mohammed Al-Sabti. Thank you so much. We can start the lunch break, and we're gonna meet at the next session. I believe it will be 12 شنو اللانش مو الحين؟ ها؟ Okay, the prayer break, only the prayer break, I'm sorry. Yeah. متى السيشن الثاني متى علي؟ And we're going to start again for the next session 12:50. Thank you so much.
Hello. Our next session will start soon.
Hello. आएगा अभी आवाज ठीक है ओके
Yes, good afternoon. Now our speaker, Mr. Mohit Naran. Mohit Naran presently working as a specialist process engineer at Kuwait Oil Company. He's chemical engineer with more than 37 years of work experience in encompassing a wide gamut of a process engineering domain, comprising upstream and midstream operation in oil and gas units, technical services in new and revamp project, dynamic and steady state simulation, process control and metering. His prime interests are in the process design of nonlinear system and application of neural network to process engineering. You have 15 minutes and your session resumes.
A very good afternoon to you. This is the first session of the afternoon. Is on reconciliation of the flow measurement errors as applied to a compression system. Now the contents, these are the contents of the presentation. Basically what is the objective, which I have already defined. What is data reconciliation and its significance? Errors in measurement, probability density function, the bell curve, the basic concept of data reconciliation, that is how do you actually do the reconciliation. Then the effects of standard deviations on data reconciliation, flow reconciliation application to the compressor unit, and then our observations and conclusions. Now the objective, as I told you, is to carry out the reconciliation on a compressor system, the flow reconciliation. Reconciliation, what does it mean really? If you take the English or the literal meaning, it is to, it's a process through which people with different opinions agree in a friendly manner. So the first condition is that there should be a difference of opinion, and then there is an agreement after a negotiation. That is what the reconciliation means literally, and that is what we will be doing to a flow compression system. It is basically, as far as the data is concerned, it's a process of rectifying erroneous data. System constraints need to be satisfied. It normally uses a mathematical model, and it works best with random errors. We'll see in the subsequent slides
what are the kinds of errors normally encountered, and the random errors. It boils down mathematically to a constrained optimization problem in which the objective function is optimized, minimized or maximized. In our case, the error is minimized and the constraints are satisfied. That is, typically it will be something like this. If A plus B is C, you will find that A is measured as 10, B is measured as 15, and C gives you 27. Now there is a discrepancy and people are unhappy. Now what do? I reconcile and I get A equal to 11.2, B equal to 14.3, C equal to 25.5. In the simplest terms, this is what reconciliation is. All the parties are happy and they are in agreement. Now what is the need for this? It's obvious from the previous example that the measured data may contain errors. There are no meters in the world which are 100% accurate. Every meter has some error, and data is often non-repeatable. You will get some changes in readings always. Some data may be missing or has not been measured. Sometimes, very often we find that flow meters, they are either not giving the correct readings or not operational, so they need to be ignored as far as the reconciliation is concerned. And the data may not satisfy the process constraints. Now, this is as applied to a compressor. What we are doing is, this is just the very basic of it. This is just a schematic shown. The differences between the true and measured values need to be minimized. The constraints of mass and energy balance need to be fulfilled. Now, the most critical requirement for DR is for the custody transfer application. Now, here it involves money, dollars. So it's very critical that both the parties are satisfied, as this is often linked to, as I told you, dollars. Now this is a small this thing on the what is repeatability and what is accuracy. Now, as is obvious, if you are right on target, you are accurate, and if you are away, though you may be having certain values which are close to each other, away from the target, then that is repeatable but not precise or not accurate. Random values you can get around the target. Now, in our case, the target would be the mean of the measured values, as we will see later on. Before that, some types of errors in measurement. Now, there are certain gross errors which are caused by some reading and remembering errors, 87.46 as 78.46, and the measurement errors are number one, the random, which are the errors of the instrument, which are the reason for that is really not known. It's an instrument error, inherent error, and there are systematic errors due to parallax or some measurements which require a constant correction factor. Let's say every time whatever reading we get, multiply by 0.98. Or there are environment factors such as temperature, humidity, etc., which also affect the metering, the flow metering especially. Currently, we are most interested, the presentation focuses on the random errors because they are the ones which can be reconciled best. So they are the instrument indicated errors, as no instrument is perfect. And these are expected to be scattered in a normal or a Gaussian distribution. So we'll see how the distribution is. and it's best applicable to random errors. Now, before we go into that, a small note on the instrument accuracy. It's often defined as a percentage at which I have 95% confidence in the meter. That means most of my readings will be, 95% of my readings will be within that range. Whether I define it as plus minus 1% or I define it as plus minus 2%. So normally the industry says plus minus 2%, and I should get 95% readings within that range. So that is my confidence level. Now, sometimes the plus minus 1% is with respect to the full scale reading. Sometimes it is with respect to the actual readings. We insist on it being on the actual. Anyway, that is defined by the manufacturers or the vendors, and it's between the vendor and the, the client. So now how the probabilities of any measurement, how are they distributed normally across the mean? So the center value is a mean value. Let's say we've taken some measurements. What you see here in between is the center value is the mean. And normally the horizontal axis is the range of the possible numeric outcomes. Let's say it's between 47 and 53, all the measurements. The vertical axis is the probability of the outcome. Now, as you can see in the bell curve, the maximum probability is around 0.4, 0.3988. And that is the case with all the distributions. No matter what you do, the mean will be around 0.3988. The rest of the distribution depends on your deviations from the mean. So this is the standard bell curve, as it is called, or the Gaussian distribution around the mean. The formula for this curve, which was developed through the Excel, I had actually taken it from Excel after putting in the data. So this is showing the normal bell curve, but sometimes it's thinner or wider depending on the deviation, on the standard deviation. If it is too much, then it will be wide. If it's very little, the values are more around the mean, it will be slightly towards the slimmer side. Now, as I told you that between x1 and x2, if it is from the mean, mu is the mean plus 1 sigma, sigma is the standard deviation, plus and minus 1 is the, the confidence level is around 68%, plus and minus 2 mu, that is 2 standard deviations, it is 95%. So we are interested in the 95% part, plus minus 2 sigma from the mean. And that is what my confidence level should be. Technically, as explained in one of the presentations earlier, this is actually 1.96 sigma and plus minus 1.96 sigma, which is approximated to 2 sigma. This is a simple example which has been taken, and for this, these are some, this is, before we go into the reconciliation, it is important to just have a grasp on the standard deviation and how it affects the reconciliation. Suppose this is the weight of a block which is measured, in grams, let's say. These are the readings. You take 7 readings or 8 readings. Basically, in actual practice, you've got to take many more. Maybe 10,000 readings, 12,000 readings. Take their average take the mean, and the standard deviation, which is calculated as per the formula, the difference of the squares of that with the mean, divided by n minus 1, which is the number of readings we've taken. N minus 1 is the correction for the Bessel's correction. It is known as the Bessel's correction. So that's why you don't divide by n, you divide by n minus 1. Now these are the probability function values for this case, what we measured. Now if you take the probability, if you ask me what is the probability of the reading, being here at any particular instance, the probability is 0. Because there are infinite possibilities, it can be anywhere. So I don't know. Our range of interest should be the probability of finding a measured variable in a range. Now that makes sense. It is the integral of this function. So it is the area under the curve, basically. And that is what happens to be 95.4% for plus minus 2 sigma. It's 68.3% for plus minus 1 sigma across the mean. The probability that a measured value will fall between plus minus 1 sigma of the mean, as I told you, I calculated for this case 68.27%. Likewise, probability that the measured value will fall between plus minus 2 sigma is 95.45%. So whatever our accuracy is, if the confidence level is 95.4%, I can safely say it is equal to my 2 standard deviations from the mean. This is a simple case to explain the concept of data reconciliation. Let's say whatever F1, F2, F3 are 3 inputs to a process equipment. F4 and F5 are the outputs which are measured. And 100, 150, 350, these are deliberately taken for explaining so that the figures are easy to add. As you can see, the inlet side is 600 and outlet F4, F5 add up to 584. So now there is a discrepancy. If I have to make payments, then it affects me a lot. So reconciliation in this case is necessary. I have just put the reconciled flow rates as F1 star, F2 star up to F5 star, and I have minimized my objective function, because every time you do reconciliation you must know what to do. You are trying to optimize, and you have an objective function for optimizing, that is minimize the error square divided by the standard deviation. Now 1 by standard deviation square or 1 by variance, as per the Gauss-Markov theorem, is the weight for the least square errors. So I am doing a weighted least square errors method. So 1 by sigma square, how much? Give me 5 minutes. I need 2 minutes. Okay. So I minimize this function subject to my constraints of mass balance. F1 plus F2 plus F3 minus F4 minus 5 should be less than 10 to the power of minus 6. 10 to the power of minus 6 is my global minima. I assume it to be a global minima. Anything below that. So the effect of standard deviation, as you can see, the deviations are, the standard deviation for the top 3 values is lower than that of the bottom values. So the result is shifted more towards the top values. The 100, 150 and 350 are closer to the reconciled values. A similar case in the next slide, as we see, if the standard deviations for the top 3 values are more than the bottom ones, then for the same objective function 0.8366, as we can see in both the cases it's the same. My reconciled total is this, and it's more reconciled towards F4 and F5. So with this concept of reconciliation, okay, I'll just, it was applied to a compressor, and the same thing was applied. This weighted least square method, it monitors the gradient, and an optimum solution is obtained when the partial derivatives are equal to 0. The input values change to the final reconciled values, but you can get trapped into local minimas. Global minima, as I told you, is achieved when epsilon is less than the weighted least square, the sum of that is less than 10 to the power of minus 6. So this is the local minima, and sometimes you will find that on both sides you are stuck up because the value increases on both sides, the derivative is 0. So you're stuck up in a local minima and you cannot get to the global minima. Now this was the actual system in which the following values were measured. Mass balance was applied across the 3 separators. And the weights, as I told you, are the inverses of the variances in the weighted least squares. I minimized the objective function, applied the mass balance constraints. The similar exercise was carried out with one of the process softwares. And we carried out the reconciliation through the process software. And these are the results. They are different because the process software also used the mass as well as energy balance. Here, as you can see, we have only utilized the mass balance. Though the measurements are based on mass and energy balance, you can see that there are subtle differences, and the results of the weighted least square methods are based only on the material balances and ignore the energy balances. The process solver carries it out with both mass and energy balance, though the weighted least square method results are based only on the measurement flow rates. Measured data is based on heat and material balance. Because measured data is a natural thing. It's based on total balance. Hence, the difference between the reconciliation done by the weighted least square method and the process software is not significant. It's within 2 to 3 standard deviations of any measured variable. Most of it is within 1. But in smaller cases, some of the cases, as you can see, it's slightly less. So that's it. Thank you very much.
Thank you, Mr. Mohit. Any question?
Yes. We are now getting the real time. Real time, right now we are in the process of carrying it out for the compressor with actual data.
Okay. Sorry, before I'm introduce myself. I'm Surya Prakash Digawali. I'm coming from company Belsim, based out of Belgium, the specialist in data validation and reconciliation technology.
Yeah.
So we deploy real-time applications for DVR, for energy management and production accounting. So when I ask you this question, dealing with real data, are you tracking it on a real-time basis on what your faulty sensors or KPIs
we will be doing it. Right now, the application, it will take time to develop it for the real time. We have taken all the data. We've got all the data through the DCS historian. Now we are in the process of reconciling, basically. So this was just a demo on how we are actually doing it.
But are you integrating it with the neighboring systems?
We will integrate it with the actual running system too.
No, not
that
just
it takes real-time data and keeps on doing the reconciliation continuously, on a continuous basis. Because this will require immense data to, actually reconcile.
Yeah, yeah.
It's not based on 7 values or 8 values.
No, it's mass balance, component balance, energy balance, power balance,
Yes.
all things in the picture.
So that's it. We are in the process of doing it, and we'll integrate it with the real-time values.
Okay. So only compressor, or you're integrating it
No,
with the whole
right
process?
now it's being done on a smaller scale. First we have to prove it, then it will be extended.
Yeah, sure. Thanks. Thank you. We can take anything offline. Yeah.
Thank you very much.
Thank you. Thank you.
Thank you. Thank you.
Thank you. Thank you. Thank you.
Thank you, Mr. Mott. Our next speaker is Andrew Jurek. Andrew Jurek is currently the CEO and shareholder of Cayman Process Solution. He joined KPS in 2018 after a tenure of 5 years as sales director at Trelleborg AB, a Swedish multinational specialized in engineered polymer solution. He managed several business units of large American corporation, as well as medium-sized the family-owned business. He has worked over 25 years in the international setting with over 15 years of experience in the oil and gas and automation industry in Europe, Southeast Asia, and Middle East. Mr. Jurek, the stage is yours. We have 15 minutes.
Thank you very much.
Thank
I'll
you.
try to stick to the allotted time slot.
Thank you.
Which will be a challenge, by the way. Thank you very much. Good afternoon, ladies and gentlemen. First of all, my name is not in the program. I'm a bit of a stand-in. You were maybe expecting 6 people to do a presentation today, but unfortunately, Mr. Erik Verloop, who was supposed to be the designated presenter today, is unavailable to be with us due to personal circumstances, so I'm a bit of a stand-in today. I would like to talk to you about quality. A lot has been said already this morning about measuring volume. I'm here a little bit to talk about the quality, specifically very important at custody transfer applications. We have designed a new mixing nozzle that is used in E-jet mixing systems for custody transfer automatic sampling systems. We've done it at the same facility already earlier mentioned by one of my previous speakers, and I'm here to present the results of the evaluation that we did. Custody transfer automatic sampling systems are described in a standard, or are described in 2 standards, but I'm here to talk about the ISO 3171, where there are 4 steps that are required to make sure that you have proper analysis of the sample that is going through your pipeline, specifically in accounting the amount of water that is being transferred. First of all, we're going to talk about the stream conditioning. Then secondly, we'll talk about the equipment. Which equipment are you using to do the actual sampling? Then how are you going to store it? How do you keep it in the condition that you've sampled it? And how do you make your analysis in the laboratory? Today I want to just talk briefly about the stream conditioning, and at the end I want to talk about the validation of the system. So my presentation will fall into 3 parts: a little bit of background on the automatic sampling. The second part is going into the results that we've achieved in the NL facility, and then thirdly also some live real-time experiences that we have with the new nozzle design. First of all, everybody knows crude and water don't mix. So if you want to take a representative sample, which is key in automatic sampling, a representative sample, on the right-hand side, the pipeline, you will either have too much water or you have too little water, depending on where you measure, at the bottom of the pipeline or at the top of the pipeline. So in order to achieve representative sampling, you have to mix your oil and water. Well, mixing requires energy. If you apply the right amount of energy, then you will achieve a perfect mixture as shown at the bottom of these type of flows. If you add too little energy, then you will either have, again, a measurement which is too high or too low on your water contents. So it is essential that in order to have a perfect measurement, you apply the right amount of energy to the stream. How do you apply that energy? Well, there are basically two methods of applying the energy to a stream. First is by using a static mixer, which uses bevel to create a turbulent flow, which afterwards is mixed properly and you can take a sample. Or you can use an E-jet mixing system. This E-jet mixing system uses a part, I'm seeing if the pointer works, you see here it takes off a part of the stream and then it pumps it around and ejects it here in such a way that you create turbulence, and then you have your perfect mixture here. And then part of the system, it will go into your receiver cans. This fast loop system is used in the same way with the static mixer, but there are pros and cons to both systems. A static mixer is an affordable solution, but it has its limitations. It is only applicable in relatively low turnaround ratios. Turnaround ratios are your lowest flow compared to your highest flow. So order of magnitude 1 to 5, 1 to 6. E-jet mixing, we have a wide variety. You always start to calculate on your lowest flow, which is the worst case condition. Then there is a pressure drop involved. A static mixer has a pressure drop. The E-jet mixing system is neglectable. Pipeline pigging is not possible with your static mixer, whereas your E-jet mixer, it is possible because the probes are retractable. They can be even retractable under line pressure. There are also some downsides to using the E-jet mixing system. You have electrical power required for your pump. You have a larger footprint, you have to put your pump somewhere, and most important, you have possible deterioration of your mixing. And predominantly the last part I want to discuss in the next slide. If you have an application where you have intermediate processes, so unloading of a tanker into a tank farm, what can happen, and this clearly demonstrates what happens, you will have pollution on your nozzles. So this is a nice clean nozzle, and on the right-hand side you see a nozzle after a couple of years of usage. What happens is that your relatively small holes of about 1 centimeter will start gradually to be smaller and smaller and smaller. This effect will cause deterioration of your measurement. The amount of energy, EA, the amount of oil being cycled through your fast loop system will deteriorate, so there's less flow, so there's also less energy added to the system, which will give you an error in your measurement of the water. So how do we address these things? How do we make sure that these little small holes don't clog up anymore? Well, one of the solutions that we've looked into is enlarging the hole. And we've come up with a new solution based on an eductor type. Eductors are already used in tank mixing, for example. And we've taken that design and applied it to our E-jet mixing systems. Initially, we've done some CFD modeling to see whether or not the solution worked. But the proof in the pudding was for us also to go into a laboratory and see these under lab conditions, how they work. We spent about 2 to 3 weeks in the Nell facility up in Scotland. We tested the new nozzle design and the traditional nozzle design under a wide variety of circumstances, both in horizontal as in vertical lines, water cuts varying between 0.1% up to 60%, and velocities between 0.1 meter per second to up to 1 meter per second. Pipeline diameters were 8-inch. And here you see an example of the test setup that we used in the Nell facility. The next sheet will show you some examples of not enough energy or just the right amount of energy applied to a stream. The first one, on the left-hand side, you clearly see the water bubbles into the oil stream not mixing with your oil. Measuring here will give you poor results. The second one, already improved. You see the water still in there, but it's starting to mix. There is not yet enough energy to make a proper mixing of your oil and water. And on the right-hand side, you will see basically a perfect mixture where we apply enough energy to the system. So, how do we make sure that the system complies with the ISO, and how do we make sure that your actually water content falls within the system ratings? Well, ISO 3171 specified 4 possible rating systems. The first one is where the best system, which is used for the custody transfer purposes, the water content doesn't vary with more than 5% of the measured water content. So your actual water content only can vary with 5%. So, for example, if your water content is 1%, your deviation cannot be more than 5% of 1%. So this is not 5% in absolute terms, this is relative to your term. So the results are in our system are shown as follows, where on the left-hand side, your vertical axis, you will see the performance rating, so your A, B, C, and D rating, and on the bottom side, basically the amount of energy we apply to the fluid. The amount of energy is expressed in cubic meters per hour. So how much pump we need, how large the pump is to recycle into your mixing nozzle so you get a perfect homogeneous mixture. The blue lines represent the traditional mixer, where the dotted lines are showing you the upper limit and the lower limit, and the solid lines will show you the trend line. The same is applicable to the orange line. And this clearly shows that compared to the traditional mixer, so the one with the holes and our new design, there is, when you apply less energy to the system, the blue line will already be even above the A rating system, whereas the new system, the new design, already shows at very low volumes, you will see it will be an A-rated system. This is for oil water mixtures with a low water cut, so in the region of 1 to 2%, and speeds of smaller than 0.2 meters per second in a pipeline. The same we did with high water cuts. Again, performance rating on the left hand, on the vertical axis, the horizontal axis will show the energy applied to the system again, where we show basically the same, is that this is a little bit different than the previous. This is not in absolute terms of cubic meters per hour, but this is relative to the theoretical amount of energy you need to apply to the system to create a homogeneous flow. So the upper line in the middle will show you the exact theoretical amount, and when we start to decrease the amount of energy, how does the system work? So on the right-hand side, you will see already that at flows of, this is a logarithmic scale, by the way, about 1.5 times less the energy theoretically required to create homogeneous mixing. The new mixing design is showing a significant improvement in mixing capacity compared to the traditional mixer. The same goes with the results in with very, very low water cuts and also with very low speeds, where the effect is even more pronounced than with the higher water cuts. In vertical lines, the difference between the traditional design and the new design is less obvious. It probably has to do with the fact that in vertical flows there is already a natural mixing of water and oil, compared to horizontal lines where you have the layering of your water and your oil content. So in this case, even though the traditional mixer is a new mixer is performing better than the traditional mixer, it is less evident than in horizontal lines. So we talked a little bit about the stream conditioning part. Now I want to talk a little bit about the overall validation and certification of the system. The ISO 3171 provides a very accurate and a very detailed description on how this has to be done. And one of the speakers after me will go into more details I'm reading, is how do we perform a waterproofing test? A waterproofing test basically gives you the opportunity to inject a certain amount of water, so a known amount of water into your oil stream. You measure it, and at the end, you will see how much water you actually have sampled, and this gives you an indication on how well your system is doing, how well you are mixing and how well you're sampling your system. Again, based on the ratings that I've discussed prior, where we have accuracy varying between smaller than 5% or lower than 15%. And at the end, there is an independent body that performs this test and will give you a certificate of your system on how well the system is performing. So how does this work? You have your baseline, you measure without water injection, then you inject your water arrives, you sample, and then you measure your baseline afterwards to see if there's any change in your baseline to make any corrections afterwards. Well, this is just an example here of the certificate that I shown you on the previous sheet, where we show clearly the volume of water, what's my baseline water amount, how much did we inject, what did we measure, and how well did it perform. In this case, there was less than 1% difference between the measured water corrected for the baseline. So if you divide those two on each other, the subtract and divide, you will have a difference, but you have to correct for the baseline in the water. We've done it with several systems. We've tested actually 3 systems, or this is an example of 3 systems that we tested. 2 of them achieved an A rating. 1 of them achieved a B rating. Had nothing to do with the new nozzle design, but with the layout of the piping system. The ISO 3171 also specifies on where you have to put your nozzles, where you have to position your takeoff point. And in this case, the piping layout, unfortunately, was such a way that we could not achieve optimal solution.
Mr. Jurek, you have 2 minutes, please.
I have 2 minutes.
Yes.
I've got a couple of sheets and I'll wrap up. One of the big advantages of the new nozzle design is that it requires substantially less energy to be as accurate or more accurate than the traditional designs. Specifically in areas where you have a limited footprint available or you have limited power available, such as on offshore platforms, these are of huge benefits. This is just an example of the system that we were able to build, where you see all the components, you see only a very small pump required for the mixing unit, and we were able to build it even inside the cabinet. So, brief summary. The E-Jet mixing nozzle proves a very promising of the new nozzle. Further testing is still required. The NEL only has the ability to work with low viscous oils, so we have to do some more testing on high viscous oils. It requires less energy, and it has a lower footprint in overall. So in areas where availability of space is an issue, where power is an issue, the new nozzle design is a good solution. Customer benefits, accurate performance, even under harsh circumstances. So where there's high asphaltenes, high wax forming, or unwanted materials, and like I said before, it requires a lower footprint and power. Any questions?
Any question, please?
Thank you. You're welcome.
Hello, thank you for that.
You're welcome.
You mentioned in your talk about the theoretical energy requirement for mixing.
Right.
Where is the traceability for that calculation?
It's specified in the ISO 3171.
That is
Calculations
for the
are there.
main line. What about a side stream, though? Because you're putting your pump into a side stream, you're not using the calculation of the main line pump. You're using the calculation of a side stream.
Now, the side stream is only there to make sure that you apply enough energy in the mainstream. So the energy required is based on the mainstream. And you pump it around, and then you apply it again to the mainstream.
This is at odds with another manufacturer who has calculations which are he calls proprietary. You have actually tested it at NEL. Your calculations have been validated?
The calculations for the amount of energy applied to the mainstream are embedded in the ISO 3171, so fully traceable back to the standard. The side stream itself, the amount of energy that for the side stream is based on that calculation, the pump size. I'm not sure if I understand the question completely, to be perfectly honest.
Okay, API 8.2 has the theoretical calculation for the mixing based upon the pumping the maximum flow of the pipeline, not the side stream.
Minimum flow, because the minimum flow will give you the worst case conditions.
Yeah, but of the main line, not of the side stream.
Yeah, but the side stream is basically, it's not relevant because it's only used to go to the sample canisters. So
no,
you don't
you're using
calculate.
it as a jet mixer though.
Yeah.
So the energy that you're applying for the mixing is done by the jet mixer pump, which is on the side stream.
Correct.
Okay, that is not covered in API 8.2.
Okay, I have to pass on giving you an accurate answer on this. Can I come back to you on this specific topic?
Yes, sure.
Okay, thank you.
Okay.
Any question, please? Thank you. Thank you, Mr. Jurek.
You're welcome.
Where's the photograph? There's the photograph. Thank you so much. Thank you so much.
I will leave the floor for my colleague, Mr. Mushar Al-Handal.
Good afternoon. The next speaker, Mr. Dr. Didier Babos. The next speaker, Dr. Didier Babos. His PhD fluid mechanics experience 35 years in field of fluid measurement for oil, gas, covering meters, proving and skid design and sizing, flow measurement, metrology operation and troubleshooting of installation, audit and inspection, training, active member in several working groups for measurement standard and regulation, like ABI, AGA, ISO, OIML. Today, engineering manager with Fora Herman. Welcome, Mr.
Thank you. 15? Okay. So good afternoon, everybody. I'm going to try to know how it works. Oops. So we will talk about calibration and condition for calibration. That means that the main point of this presentation is to focus on product we use to calibrate the meter. You know, we are meter manufacturers and we calibrate all meters we produce. And for us to be very direct on the topic of this day is it does not make sense to calibrate a meter on a product which will not be used on the field. So for a given application, the good approach is to calibrate on product for the application. We have a lot of application with water, like water injection. Okay, so it makes a lot of sense to calibrate on water. But if the application is for crude oil, like 20 centistoke or even at 2 centistoke, it does not make any sense to calibrate on water. Water is a good fluid for water application. So all meters are more or less accurate and more or less sensitive to a lot of parameters. Okay, a meter can be very accurate, very reliable, very robust, but each meter must be periodically calibrated. I heard some stories about, okay, with this new meter, we don't have to calibrate during 5 years. Oops. Okay. So that means that if something is wrong with the meter, the day following the calibration, you will make mistake during 5 years. It's big. So the meter must be calibrated at the beginning and periodically to check if everything is okay. So meter performance, when I talk about performance, we all understand that we talk about linearity and repeatability, which is a very health approach for meter. And this morning we was talking about uncertainty, and everything is going into this famous uncertainty. So this performances depends on flow rate, temperature, pressure, upstream, downstream, pipe section, blah, blah, blah. We know that. Depending on the meter type you use, we have different effect. And also depend on fluid characteristic. Now we know that all meter type are Reynolds sensitive. A long time ago, 10 years ago, we was talking about, okay, this meter is Reynolds sensitive, this is not. It's not true. All meters are more or less Reynolds sensitive. So Reynolds means viscosity. So that means if you don't calibrate at the good viscosity, there is a possible error or mistake or bias. So this is why verification must be done as close as possible to process condition. There is a very good application, mainly in the US, where we have a meter, you have a prover. So it's easy. Each time the meter is proved against the prover with the exact process condition. In another application, we cannot do that because we need some more places, because it's very expensive, because the prover will be too big. So we find some other approach, like a master meter, which is a good one, but the master meter must be proved as well. Or other application, which is remote calibration in a central facility. It's working very well, as long as, one more time, the meter is calibrated with the fluid in process. Okay, so it's exactly what I was talking about. Sometimes it's comfortable. We have the prover close to the meter. We can prove when we want, twice a day, every hour, or, okay, if 1 degree difference. But on other applications, it's not possible. So we have to be sure that the meter, and at the less important degree, the master meter, if we use a master meter technique, the master meter must be calibrated under process condition. So process envelope is defined by flow rate, temperature, pressure, fluid density, fluid viscosity, water content. I guess that's the majority of our concern are here. So, first of all, starting with flow rate, we have to cover the full flow rate for the application. It does not make sense to calibrate a meter on a very small turn down if it is used. Typically, the flow rate, we start with the manufacturer standard. So typically, all manufacturers work with a 10-to-1 turn down. Okay, they propose PD meter, ultrasonic, Coriolis, on a 10-to-1 or even more turn down ratio. Okay, that's fine. But what about the application? Your application don't need a 10-to-1 turn down, maybe. So why not asking the manufacturers to calibrate on your target, to be more, to have a bigger resolution? So in other words, it does not make sense to have only 3 points here on your application, when you can ask the manufacturers to have 6 points in your application, which make more sense, mainly if you want to linearize or if you want to do a more accurate uncertainty analysis. So focus on the application and only on the application. So the other point is how to compensate for pressure, temperature, and so other variable we have in the field. So the API defines some correction factor, typically applicable mainly for liquid. Okay, we have CPL and CTL, everybody know that. And we have mechanical effect of temperature and pressure on the prover, but nothing on the meter. So if the meter is sensitive to temperature variation or pressure variation, we don't have a lot of application for that. We don't have a lot of answer. Why? Because focusing on temperature, the impact of temperature is more important on viscosity than on geometry. So if a meter is sensitivity to viscosity change, it is very difficult to adjust or to compensate for temperature change, because the most important effect is not dilatation, expansion, it will be the viscosity which will change. So when the meter is not very sensitive to viscosity change, it becomes possible to determine a coefficient allowing to compensate for temperature variation. Temperature variation means temperature variation between the proving condition and operating condition. That means, one more time, you don't have the prover close to the meter. So when the meter is not very sensitive to viscosity change, that means there is a lot of meter like this, ultrasonic, Coriolis in some region, and turbine meters, helical turbine meters, which are, everybody knows, less sensitive to viscosity change than conventional turbine meter. It becomes possible to calculate a coefficient allowing to compensate the difference in temperature between proving and operation. One more time, the idea is to be as close as possible to operating condition. So, an example, we calibrate a meter at 104 degree F, which is a little bit more than 40 C. I don't have the translation in my head, but and we can produce, as long as the meter is not sensitive to viscosity variation, we can produce the performance curve corrected at 60 F or 15 C. It's important when you have an application, you know, when you send the meter back to the lab for calibration, and you use this meter without any other calibration option. So you can obtain this curve. Talking about pressure variation, one more time, if there is a difference in pressure between calibration and operation. So all meters are submitted to pressure, so they are submitted to geometry variation, if the pressure increase or decrease. So if you use double case envelope, which is applicable on typically on PD meters and on some turbine meters, with a double case design, the same pressure is applied in both parts of this tube. So that means that if the pressure increases, we don't care. We have the same pressure on both parts of the tube. So there is no effect on pressure. Hello? What about, so we talk about flow rate, we talk about temperature, we talk about pressure, so what about the upstream and downstream section? We know that some technologies are very sensitive to upstream and downstream pipe section, some others are not. PD meters are not sensitive, okay, end of the story. Coriolis meter is probably not very sensitive, depending on recent research. Ultrasonic is sensitive to upstream condition. Turbine meter is sensitive to upstream condition, and for sure orifice and differential pressure measurement. So when the idea is to calibrate remotely, the idea is not to calibrate the meter, but the meter run. Why? Because one more time, we need to reproduce the operating condition. And if we want to reproduce the operating condition, we need to reproduce the flow profile, the swirl, in the lab and in the field. So that means that the complete meter run must be used to calibrate the meter in a lab. Here we are in a lab, okay? I don't know this lab, but we have a very clean situation. We have probably 50 diameter upstream and 20 diameters downstream. It's a dream. But when we arrive at the site, we are here. So it does not make sense to calibrate the meter here if you want to use it here. Or you have to consider a big uncertainty and a big shift between your calibration and operation. It's why we can consider the meter run. And then we remove the meter run from the skid on the installation and put the full meter run on the lab to reproduce the same configuration. This is one application which looks big because the pressure is high, but typically we can consider that. This is typically a 4-inch meter, and for the application, the pipeline is 8-inch. So we have a contraction, we have a flow conditioning section, we have the meter, another conditioning section, and then expansion. So we reproduce that on the lab. Other meters, this is typical application for Coriolis mass meter. For deposit and for gas, it's not recommended to use other configuration. So the flag design is recommended. So this is installation. And when we look at calibration, frequently we see that. So that means that there is no difference. Okay, so for sure the manufacturer will explain you that, okay, that's fine, we don't care. But it's trouble for me. So, now talking about viscosity and density. Mainly viscosity, because the meter is less affected by viscosity than for density. So we have a good guy, Mr. Reynolds. We talk about him a lot of time, but sometimes it's good to have his face in front, So the viscosity of the product affect meters, more or less. Some meters are not very affected, some are really affected by viscosity. So in any case, first of all, you have to be sure that the meter you select will cover the Reynolds application. Okay? By the way, we use different products. We have liquid, hydrocarbons mainly. We have gas, and we have water. And I want to be back on water. A lot of labs and manufacturers use water for calibration. It's obvious. It's cheaper, safer. We don't have any ATEX issues with water. It's available, and according to the assessment, it covers everything. No, it don't cover everything. If you want to use a water meter, for sure, calibrate it on water. But if it is on hydrocarbon, and when the viscosity grow up, is more than 2, 3, 4, it's mandatory. So water, what is water? We use water to clean, to drink, for a lot of application. And back to chemical and physics, Here we talk about another point, which is the velocity of sound in fluids. So the velocity of sounds, mainly used by ultrasonic and so on, varies depending on temperature. And talking about fluid, we have 3 fluids. We have liquids, when the velocity of sound decreases when the temperature increases. We have gas, when the velocity of sound increases when the temperature increases. And in between, we have water. Water, it's a mixed, so it's a very specific product. So, in some case, we can say, okay, we have to cover the Reynolds number. It's not true. Let's say an example. 3,000 to 12,000 barrels, 10-inch, this viscosity range. So we calculate the Reynolds range. Okay, so first option, we calibrate on product and we cover the Reynolds range. Second option, we have on water. And to cover that on 10-inch pipe, we have to respect a minimum Reynolds at 0.1 feet per second, which is very low. And the maximum Reynolds number will be at 70 feet per second in liquid. It does not make sense. So it does not work. So a quick one. 1 minute more, 2 minutes. So this is a calibration of a turbine meter, a conventional turbine meter on water. When we use on product, oops. When we use a different viscosity, oops. One more time, the true red line was covered on water. Another application, for 3-inch Coriolis meter. initial on water and then on product. Anode an 8-inch, water and product. So I don't recommend water for all application. Thank you for your attention.
Thank you very much. Any question? Any question?
It's good.
Okay.
Ooh, wonderful. Thank you. Thank you. Oh, yeah, safe.
Our next speaker, Mr. Pariksit Engineer. Actually, his last name is Engineer. I didn't believe it until he showed me the passport. That's a nice name, by the way. Mr. Pariksit is the field of custody metering from the last 15 years, presently working as business development manager. He has worked at all levels, varying from a software engineer to project manager, and has acquired the knowledge of oil and gas by getting involved in field activity. The stage is yours. You have 15 minutes. Thank you so much.
Good afternoon. Good afternoon. Okay. So actually my colleague Mr. Ben Lich was supposed to be here to present this paper, but due to some circumstances he could not make it here, so I'm here. Anyway, I'll start, because since morning we are discussing on a lot of metering aspect, and today's world is all about information and managing information. So what I have seen is like we are talking a lot about technology and how to get the best information generation, like accuracy, how accurately we should measure all those things. But nowadays it's all about information utilization. So in my presentation, what I'm going to present is like we have information in metering systems, but if it is presented to right people, right level, then it will be more beneficial. Decision making will be, more easy and fruitful. So once my presentation will start, I will go through it. Yeah. No, by my name. Yeah. Sorry guys,
Very sorry, gentlemen.
Welcome back.
The presentation is not ready yet. We're going to present the last speaker, swap it with Mr. Pariksit, Mr. Nishant, and Mr. Ali will introduce him.
Sorry for that. Next speaker will be Mr. Nishant. He's mechanical engineer having experience over 32 years in the area of erection and commissioning, maintenance, validation of metering system, calibration of storage tanks with major experience in metering, maintenance, validation. He has been in KOC since last 2 years and is currently responsible for preparing and rolling out the KOC standard for crude oil measurement, which compares of 9 parts. Mr. Nishant, you have 15 minutes.
Which one is forward? Forward. Good afternoon, everybody. My today's presentation is basically a study on various variables that influence the flow measurement through orifice measurement system. So basically, in order to understand what are the parameters which are affecting the flow measurement through orifice metering system, we need to first find the equation or analyze the equation to see what are those parameters. If you refer to API 14.3, API MPMS 14.3, the mass flow equation for the orifice system will be given by this. The coefficient of discharge CD multiplied by 1 by under root 1 minus beta raised to 4 into epsilon pi by d square divided by 4 into square root of 2 times rho Tp into delta P. Now in this equation, we see the parameters which are affecting. One is the beta ratio. Beta ratio will be denoting that the orifice diameter and pipe diameter are 2 of these parameters. Another one is the delta P, which is the differential pressure. Then rho Tp, rho is the density at flowing conditions. So we don't find here pressure, neither we find the temperature in this equation, but they too are responsible for the measurement. If you see in this slide, this gives 7 basic parameters which are required for computing the flow through an orifice metering system. Now I am referring to flow measurement of a crude oil. Now I have considered variables, meter tube, bore, meter tube diameter 14.9536. These are the values I have considered for computing the flow, and the calculation results are shown as under. What I have done is I have changed the meter tube diameter by some percentage, 0.5 to 3%, something like that, and that has an impact on the flow measured. So how much is the impact that I have tried to evaluate? That evaluation has been done through an Excel spreadsheet. Before using this spreadsheet, I have verified the spreadsheet through 2 independent softwares, flow calculation softwares, and also through a flow computer. If you see the first parameter, which is the pipe diameter I have considered. So the pipe diameter, original pipe diameter was 14.9536. I varied it from 0.5 to 3% in the positive direction as well as on the negative direction. The value which we get is shown in the next column. And I use the same software, the Excel spreadsheet, to calculate what is the volume. When I see the pipe diameter variation, at 3%, it is something like minus 1.31%. Meaning, with the change in the pipe diameter by 3%, the impact will be on the negative side, approximately 50% of that change, which can be seen from the next slide. The blue bars show the change in the parameter, which is the pipe diameter in this case. And the red bar shows the impact in the flow measured. The next parameter is orifice bore diameter. If I change the orifice bore diameter again from 0.5%, 0%, 0.5, 1%, 1.5 like that,
In both directions, positive and negative, I get the value for the orifice bore, and the impact can be found out as positive impact for the positive change in the orifice diameter, which can be understood from the graphically. So with a change of around 3%, you can see the percentage change in the volume calculated will be something like 7.64%, which is highest impact which we can see from all these parameters. You will come to see in the next slide. The next parameter was the differential pressure. When we change the differential pressure again from 0.5 to 3% in both directions, we will see the impact on the flow. The impact here is almost similar to what is the impact due to your pipe diameter, but only in the reverse direction. With the increase in the pipe diameter, we were resulting into negative flow, keeping all other parameters constant. Whereas in case of DP, if you increase the DP, there will be increase. The impact will be increase in the volume measured. So this can be seen. The next one, the next parameter is the pressure. If you see the impact made by pressure, if you change the pressure, percentage change in pressure by 0.5 to 3%, you will see that it is having a very marginal impact because we are talking here of crude oil, and crude oil is incompressible. That is the reason. If you are using gas, probably it will have some impact. So for 3% change, it's merely 2 barrels approximately, which is 0.002%. And you cannot see even the red bars, because the difference is very, very small in the volume. Next is the impact due to temperature. So again, the same changes have been considered, 0.5 to 3%, and we see that the impact due to temperature, for 3% it is only minus 0.09%, which is 131 barrels. Or if you see, 100 was the temperature. If I consider 103 as a temperature, this impacts into 131 barrels, which is equivalent to 0.09%. Again, we can slightly see the red bars, which is a very small impact which it is making. If you see the impact due to API, API is having some impact, which can be seen as around 3% change in the API will lead to something like 373 standard barrels per day, which is equivalent to 0.27%. With the change in viscosity, we see that the viscosity is having an impact, but again, it is very small impact. For 3% change in the viscosity, we can see something like 0.02%. Again, here we won't be able to see the red bar because of the small change, very small change. Now, if we analyze the overall impact because of these changes, the change is same for all these 7 parameters from 0.5 to 3% in the positive and 0.5 to minus 3% in the negative direction have been taken. We see that for 3% change, if you see the pipe ID contributes to something like minus 1.31%, which is considerable. The orifice bore diameter is contributing maximum. The DP is also contributing 1.48%. So meaning the primary measurement, the parameters which are responsible for the primary measurement are contributing maximum. If you see the fluid properties, basically the API and the dynamic viscosity, they are contributing marginally, but the volume correction parameters like pressure and temperature
they are contributing even less than the parameters responsible for the fluid properties. So if you closely observe this, the volume correction factors are contributing around half of the impact which is contributed by API and dynamic viscosity. So the conclusion is the impact on the flow measured is maximum due to the change in the orifice diameter. The other two elements, namely the pipe diameter and the differential pressure change, also impact significantly on account of the fact that these are the parameters used for the primary measurement. The combined impact due to the change in the parameters that determine the fluid properties, namely viscosity and density, is comparatively less. But the combined impact due to change in the volume correction parameters is minimal, even less than the combined impact due to parameters that determine fluid properties, which are viscosity and density. Any questions?
Thank you, Mr. Nishant. Any question? Thank you very much.
Thank you. Thank you. Thank you.
And our last speaker is Mr. Pariksit Engineer. Welcome again. Mr. Engineer, you have 15 minutes.
Thank you.
Floor is yours.
Sorry, guys. I think because of some confusion. So actually, Ben was supposed to be here to present, but he could not make it, so I'm going to present myself, Pariksit. So today we are going to talk on IMET. It's a new solution in the market, we can say, is because so far we were talking about information in the metering control room. But what we are going to talk about is MIS for metering systems. So I'll go to basics a little bit. What is custody transfer? What is custody metering? Custody metering is the point when exchange of commodity happens. And metering point, great importance is accuracy and what data we report. So custody metering components are like we measure in the field, then we do computation in the control system, then we represent it and historize this, then we generate a metering ticket which will say what quantity deliver and what was the quality, and then that's all about metering control system. But metering control system is not only this, but in order to perform, we need all these other tasks also to be done. We need to make sure that our systems are up and running. We need to make sure that systems are accurate enough by doing validation. We need to do regular maintenance so that whenever systems are required, it is available for operation. So this is the present day metering system. Flow computers are connected to field device. Flow computers are connected to supervisory. And what all it does apart from this, like it helps in reporting correct quantity and quality. It helps us is monitoring. CBM, some places yes, some places no. Will it do health check? Maybe say yes, maybe say no. Will it do validation? Uncertainty monitoring? Generally, it is the process which is done offline. Like people used to go do calculation check, uncertainty calculation also is done on offline. Then will it do maintenance scheduling? No, it's also a manual process in which somebody has to keep track of things which is to be maintained. Somebody has to maintain record. Does it handle mismeasurement? No, it doesn't. That also is a separate process. And dispensation and asset management. So far, we are gathering all the information, but further, all the tasks which is required to make sure that we are delivering right quantity and reporting right quantity is not done so far. So, what is IMET? In nutshell, like we can say, it's a management information system. It will bridge the gap between information available in the local control room to the information which can be made available to the management level. So how is the system architecture? On field, it's a traditional metering supervisory control. Then we connect it to a global system, we can say cloud or a central server, which will pick up data from all the scattered metering systems and process it. And it can be made available in a very user-friendly dashboard form of data. So here we have shown world map, but it can be map of Kuwait, and means we can make different provinces. And if you see, there is one green area and one orange area. So what it highlights is green area is all okay, everything running fine. Orange area means we need attention. Red area means we need urgent attention. And how we derive to this is, it will calculate online uncertainty, real time. It will calculate the exposure in terms of throughput. Because in earlier presentation we said that suppose my throughput is high, but error percentage is low, my exposure is more. So sometimes we see uncertainty figure which is very small, but it is giving more exposure. So considering all that, it will give you indication that you need an urgent attention. So it's an interactive map. You can click on it and it will further expand. Okay, before going into the uncertainty, I will say it will also maintain inventory. It's a kind of asset management. So it will tell you how many Coriolis meters are there, how many orifice meters are there, how many ultrasonic meters are there. Then we can further subdivide into region-wise, then manufacturer-wise. You can also maintain inventory details, like when calibration was done, what maintenance is required, what is data sheet. So all the information is available on fingertip. Then it's a regional area-wise health indication, as I told you before. It's an interactive map. So if you click it, it will go further down. So it will say, suppose we are doing mass-based flow rate calculation. So it will tell you, in particular that region, this is the uncertainty we are exposure because of this mass measurement. And then if you further drill down, it will tell you all the component which is contributing to uncertainty. So suppose your temperature transmitter is not calibrated, and if it is contributing to an uncertainty which is having some exposure, it will tell you this is the piece of element wherein you need attention and you need to correct it. So it will help decision makers to take action. It will help to monitor things in a better way. Then you can also maintain records, like you do prover validation frequently, or your prover validation is due. So you can schedule here. Also you can maintain history here about prover validation, what was my last volume. So this can be maintained here. It also do keep record and keep scheduling of when validation is required. Suppose you finish validation, you can update in the system and that can be made available at the fingertips whenever it is required. So sitting in the central office, you can monitor whole region, you can look into asset, you can look into what exposure I am running into, whether my validation is completed properly or not. Further to that, sometimes we have a mismeasurement. So it can also be handled in this system. We can make record of mismeasurement report and whether it is cleared or not cleared, accepted or not accepted. Then sometimes we go to sites and we say that, okay, my system is 5 years old, but I don't have FDS. I don't have data sheet. So this system can be repository of all the data, all the documentation required for the control system, or say full metering system. So feature of this is fully scalable. Like I have shown you various features like asset management, then instrument list, validation, record, scheduling maintenance, training maintenance. This all can be in bits and pieces. Like you can choose only a module. Like suppose I want to have only uncertainty module. So that can be purchased. So the main features are it's a comprehensive management information system package for metering supervisory. It gives you easy to interact, easy to understand dashboard view. It is having live uncertainty built, and live uncertainty means it will refresh every 20 to 25 seconds. It's not like you do uncertainty calculation after 6 months and then you come to know. And at that point of time also you don't know when that error was occur. So here if something goes wrong, immediately you will come to know. Asset management, predictive maintenance. You can also pick up data from ultrasonic meter and built-in CBM into this. So it's a fully modular and, based on the requirement, it can be evolved to your requirement. It is a multi-level from, suppose we want to do only some few control rooms, that can be done. It can be bring up to corporate level. So actually, IMET name is like eye on your metering system. So once server is placed, then on inbuilt intranet, web page is available and it can be further drilled down into this. So with this IMET plus traditional metering control system, will it do reporting correct quantity and quality? Yes, with IMET and metering control system it is possible. Does it monitor the control system? Yes. Does it help in health check? Yes. Will it help in doing validation and recording, maintaining recording? Yes, it is achieved. Will it help in scheduling maintenance and maintaining record in one place? Yes, with IMET it is possible. Handling mismeasurement? Yes, with IMET it is taken care. Dispensation and asset management. So in short, with this solution, like at fingertips you have all the information available and you can keep better watch on your metering system. Okay, so any questions?
Any question for Mr. Engineer, please? Thank you so much.
I'm available here if you have any question. Please do contact me. Thank you very much.
Yes, of course. Thank you. That was the last presentation for the day. Tomorrow we're going to start the first session at 8:30. And please, you are very welcome to our lunch break. Thank you very much.